感谢于市长，感谢北京市一直以来对北京人工智能发展和智源研究院的大力的支持。下面我们正式进入大会的报告环节。智源研究院自成立以来，积极地探索新兴科研管理等体制的机制的创新，已经在创新研究、学术生态、成果转化等方面取得了重大的进展，而且取得了一系列的研究的成果。下面有请智源研究院黄铁军院长代表研究院简单的汇报一下过去1年的建设进展。铁军。
尊敬的吴部长、于市长、各位专家、各位领导、各位代表，1年1度的智源进展报告是我最想跟大家汇报的，也是最高兴的这么一次报告。1年来呢，在大家的支持下，智源研究院又取得了新的成果。那么，我们先从今天大家可以说最热门的这个词开始汇报起，通用人工智能。那么有2个解释，一个呢叫 GAI，General Artificial Intelligence， 另外一个叫 AGI，Artificial General Intelligence。我想大多数咱们媒体大家理解的应该是第一个。确实，我们现在已经进入了通用人工智能时代。但是呢，在人工智能领域谈了20多年的是 AGI， 我们正在往这样的一个终极目标前进。所以目前呢，我们就处在从 GAI 往 AGI 迈进的这样的一个历史时期。要实现 AGI， 在过去的几次智源大会上，每年我们都会讲有3条技术路线。那么第一条技术路线，大数据加今天大家都在用的自监督学习加大算力形成的信息类的模型。第2种，基于这个虚拟的世界或者是真实的世界，通过强化学习来训练出来的具身模型。还有第3种，那就是直接抄自然进化的作业，抄答案，就是直接复制人脑，复制一个数字的一个电子版本的这样的一个智能体出来。这3条路线呢，在全世界方面的都在进行。其中，当然所有的目的都是为了实现 AGI。其中呢，第一个是今天最热门的一个机构 OpenAI 做的 GPT， 第2个是另外一个机构 Google DeepMind 的 DQN 深度强化学习网络为核心的，取得了一系列的进展。智源研究院呢，作为一个在通用人工智能方向一直在努力的机构，有一个不同于他们2个的特点，就是从第一性原理出发，真正的构造一个如果是从梦想的角度来说，从原子到有机分子到神经系统到身体的一个完整的这么一个智能系统 AGI。当然，这是一个大概要20年的目标才有可能实现的。那么在作为一个新型研发机构平台，那我们呢，其实在3个方向都在开展工作，也是今天我要给大家汇报的重点。第一个呢，就是大模型方向；第2个呢，具身方向；当然还有刚才说的这样的一个特色方向的进展。大模型这样的一个时代，大概在2018年就开始了，也就是智源研究院成立的那一年，就成为了全世界的一个大家公认的这么一个方向。在这个方向上，我们率先汇聚了 AI 领域的顶尖学者，我们叫智源学者，开启了大模型的探索，率先组建了大模型的研究团队，成为今天中国大模型研究的主力，率先预见了大模型时代的到来。包括大模型这个名词，就是2021年智源研究院发布悟道 1.0 的时候正式提出来的。 然后进入大家的这个视野。我们率先发布了悟道大模型，率先启动了大模型的测评旗舰项目，服务于大模型的行业的发展。我们率先呢倡导大模型开源开放，发布了 Flag Open 大模型开源系统，率先构建大模型的生态，包括今天的智源大会，还有10多万人的智源社区，都是大模型技术研讨的一个高地。其中呢，2021年6月份发布的悟道2.0的大模型，当时是我们国家第一个，也是当时全球最大的大模型，1.75万亿参数的大模型，在国际范围得到了广泛的反响。当然，现在大模型已经成为全社会关注的热点。那什么是大模型？我们认为呢，至少有3个特点，一个是规模要大，网络参数，神经网络的参数呢要达到100亿规模以上。第二个要有涌现性，这是人工智能发展60-70年来，今年可以说是最里程碑的这样的一个新的特性，就是涌现性，产生了预料之外的新能力。一个模型如果只能从原有的数据、原有的算法就能推导出来的结果，那不叫涌现。涌现一定是有全新的功能出现才可以。第三个就是通用性，它不限于专门问题或者专门的领域，具有通用性的，能够解决各类问题。当然，受限于模型目前的阶段，也不能说所有的问题都能解决，但是呢，它有很强的推广性。那么今天呢，我就特别高兴宣布，智源呢正式推出全面开源的悟道3.0模型。第一个呢就是视觉大模型，是系列大模型，视觉的系列大模型。今年以来，智源呢连续发了6个视觉大模型。第一个呢是叫当时最强的10亿参数的视觉基础模型伊娃。通用性是它的最重要的特点。这个模型呢，通过语义学习和几何结构学习相结合，解决了视觉模型的通用性问题。在ImageNet 分类、COGO 检测分割、Kinect 视频分类等广泛的视觉任务中取得了当时最强的性能。这些任务当初都要一个一个的专门的模型去做，我们靠一个通用模型实现了所有的这些专用模型的功能，而且呢性能比他们还要强。这样的一个多模态的在这个基础上又训练了伊娃 Clip 的这样的一个多模态的预训练模型，是零样本学习的一个基础模型。在今年年初发布了5个 billion 的版本，创造了零样本学习性能的新高度，超越了此前最强的 Open Clip 模型。在 ImageNet 的 1K 零样本达到了Top 1，达到了82%的准确率。那么去年发布的伊娃 Clip 1 billion 版本，今年才被 Meta 发布的Dino 第2版模型追平。那么我们都知道，语言模型可以问答，视觉模型怎么提问？在这方面呢，我们率先提出了图像理解图像、图像解释图像、图像输出图像的理念，把自然语言处理中的上下文学习的思想引入视觉模型。那么提出了通用视觉模型 Paint， 以视觉为中心，作为整个建模的核心思想，将图像作为输入输出的模态，从而获得上下文的视觉信息，完成各种视觉任务。今年4月，智源推出了首个利用视觉提示完成任意分割任务的通用视觉模型 SegGPT， 一通百通。SegGPT 呢，应该说是通用视觉，我们的大模型进入通用视觉的一个里程碑。这个模型发布的时间和 Meta 发布的 Sam 是同一天发布的，碰巧撞车。这2个模型呢，都是通用视觉方面的可以说里程碑。那么 Sam 模型呢，它最大的特点叫一出即通，点一个点 简单的点一个点就能把这个物体精确的分割出来，这是可以说完美的解决了传统的图像分割问题。但是呢，这是一个物体 ，SegGPT 呢是一通百通，可以分割任意的物体，包括物体的任意的零件，甚至于一个物体的不同的表面，只要你是一个相对这个具有物理意义的这个结构，它都可以这个分割出来。这是一些例子，它可以做视频，所以这是第一帧视频选中。如果你关注的是视频中的运动物体的话，那所有的这些运动物体呢，都可以不用任何人的操作，就全部呢给自动的这个分割出来。所以强大的通用能力、灵活的推理能力和自动视觉的分割能力，可以说我们已经达到了通用视觉的一个里程碑。那这样的一个技术，这样的一个模型呢，在自动驾驶领域，在机器人领域，在我们实体智能领域，一定会发挥基础性的作用。当时发布这个模型之后，就有很多这个用户关注能不能做零样本的视频编辑，因为这也是这个传统在图像视频领域很重要的一个应用。那我们呢就实现了零样本的简单提示，提示还是需要的，你到底要做什么，对吧？提示还是需要的，但是不需要你提供样本去训练它，这个模型就可以完成我们原来的这个各种这个视频的编辑任务了。在这个基础上呢，我们进一步扩展了一个新的模型，一个接受多模态的输入，产生多模态输出的多模态大模型。这个模型呢，能够在多模态的序列中补全一切，而且能生成多模态的预测。我就请大家看这么几个例子啊。左上角的这个第一张图，这个模型呢，你给它这张图，它不是说给你解释这里边有太阳、有水、有船，它上来就告诉你这是莫奈的日出印象，然后给了很多认知意义上的解释。左边的第二个例子呢，是能够完成少样本的图文的理解，给2个图文对儿作为例子，模型呢就自动的完成任务。它知道你要干这样的事儿，对吧？给2个例子，那个比如说大熊猫是一个中国的这个国宝，中国人都很喜欢。好了，你再给个皮卡丘，它就会说皮卡丘是日本的一个明星的这个动画。日本人都很喜欢这个角色。还有呢，这个模型呢，能够根据图片或视频进行问答和多轮对话。在零样本的 COCO 图像的描述性能，达到了109，超过了 Flamingo 80 billion 的84。右边这张图呢，展示的是生成能力，比如呢，根据任意长度的文本可以生成图像，这个大家现在很多都有了啊。中间呢是一个图生成，图生成是什么意思呢？就是你给它一对图像，它开始推理。比如说，这个左边给一个小狗的下面那个图啊，给一个小狗的图像，加上还有另外一幅老虎的图像，它就猜你可能要一个狗形状的老虎，所以就产生了一个狗头老虎的这样的一个图像，叫虎头的这样的一个图像。右下角呢是在多模态上下文中的生成，根据文本和图片的对作为提示呢，生成融合上下文信息的一个新的图片。这个图片是理解了这2种模态之后产生的一个这个新的图片以及相应的描述。还有更多的能力，我们还在挖掘。我们也希望呢，尽快呢有更多的这个合作来挖掘这种可以说多模态模型蕴含的无穷无尽的潜力。所以总的来说呢，把上下文类似于语言这样的上下文的一种学习能力引进图像之后，其实有更丰富、更让大家兴奋的新的这种通用智能呢，能够激发出来。语言模型可以说是大模型中 现在竞争的这个热点。那悟道 3.0 呢，我们今天呢正式发布语言大模型悟道天鹰和对大模型进行评测的一个体系，叫天秤。悟道天鹰 Aquila 语言大模型呢，是第一个中英文双语支持商用、符合数据合规要求的数据大模型，所以大家可以放心的去用，还可以放心的商业化。因为智源是一个非盈利机构，我们就是为这个行业发展提供公共的这个技术的。天鹰的这语言大模型呢，是在一个中英文的高质量的合规的语料数据库基础上，从零开始训练的一个模型。通过数据质量的控制和多种训练的优化，实现了在更小的数据集、更短的训练时间，获得比其他的开源模型更优的性能。这是一个系列模型，我们会这一次呢，我们这个发布的是7B 和33B， 就是70亿参数和330亿参数的基础模型，和 Aquila Chat 就是对话模型，也是这2个参数规模，以及呢 Aquila Code 代码模型、文本代码生成模型。后续呢，这些代码模型以及呢这个升级的都会开源。Aquila 基础模型呢，技术上继承了 GPT-3、Llama 等的架构的这个优点，那么替换了一批更高效的底层算子，重新设计了中英文双语的 Tokenizer， 升级了 BM Train 的并行训练的方法，在 Aquila 的训练过程中实现了比 MacTran 加 DeepSpeech Zero 2近8倍的训练效率的提升。所以我们有信心后续给大家提供更大规模的这个更适合这个产品化的模型。这个模型呢，已经具备了很强的这个能力，对话能力。比如这几个例子里边，最左边的例子，问他能不能带着炸药上飞机，他马上提醒你这是违法的行为，违反了什么这个规定。中间这个例子呢 ，sorry， 中间这个例子呢是用对话的方式，这是个语言模型，它理解了用户的意图，然后调用图像生成模型，刚才说的那个生成模型，来生成一幅图片，比如说帮我生成一个这个唐装的图片，帮我生成一个机器人的图片。如果在生成的图片过程中你觉着不满意，没关系，你直接告诉他就行了。比如这个例子里边，先生成了一张人脸的图片，说他的眼睛不好看，换成蓝色的，他给你换成蓝色的。说这个肤色呢不够白，他就给你变白。所以你有什么需求，你就直接告诉他，这个模型呢就帮你完成这些设计任务了。在技术上呢，我们这个训练过程中实现了模型能力和指令微调的循环的迭代，包括对数据集的高效的筛选和优化，充分挖掘基础模型的潜力。Aquila Chat 呢支持可扩展的特殊指令规范，可以根据你的需要再增加，比如说你的这个设计任务一些比较体系化的指令，你可以把它这个定义出来，然后这个模型呢就按照你的这种工作的要求来自动帮完成任务。那么刚才我演示的背后的这个图像生成和这个图像的调整修改功能呢，用的是我们去年发布的 Auto Diffusion 8种语言，今年升级为18种语言的全球支持语言种类最多的一个这个图像生成模型，也已经进入了国际上这个最热门的这样的一个图文生成模型。因为支持的语言多，很多国家的用户呢都可以用这个模型来生成这个他们喜欢的图像。代码模型，基于 Aquila 这个7 billion 的这样的一个基础模型，Aquila Code 也是7 billion 70亿参数，用小数据集、小参数量实现了高性能的，目前是支持中英双语的，也是应该说是性能最好的一个开源的代码的模型。 那这里边的所用的数据代码经过了高质量的这个合规处理，使用这个合规的这个开源的许可代码进行训练，所以呢，大家可以放心的让用于我们的这个软件开发这样的一些任务。Aquila Code 7B 分别在英伟达的和国产的芯片上完成了模型的训练，而且呢，通过对多种架构的代码和模型的开源，在很多就是无论你是什么样的一个软硬件的组合，这样的一个代码模型呢，都可以部署。这个呢就是刚才演示过了的，去年发布的9种语言，今年升级为18种语言的一个，在这个文图生成领域，国际上也影响力很大的一个Auto Diffusion 模型。下面呢给大家这个报告一下大模型评测的工作。那这项工作呢，大家都知道，今天全世界范围中发出了这么多模型，到底哪些模型好？哪些模型在哪些方面好，哪些方面还存在不足？那么我们在这个科技部大模型的这样的一个旗舰项目的支持下，今年1月1号这个正式启动，中的可以说第一件重要的任务就是这个推出了大语言模型的评测体系，叫天秤。这样的一个大模型体系呢，目标呢就是建立科学、公正、开放的评测基准、方法、工具集。协助研究人员全方位的来评估基础模型以及训练算法的性能，同时呢，我们也在探索利用 AI 方法实现主观评测。我们现在客观评测、主观评测同时在进行，同时呢，也希望用 AI 做 AI 用 AI 来减少这个主观评测的这个工作量，大幅提升的评测的效率和客观性。目前呢，天秤大语言模型评测体系，在能力、任务、指标这样的一个3个维度上，建立了可以说是一个全方位的评测体系，包括30多种能力，就是语言大模型可能具备的30多种能力，加上5种任务，再乘以4大类的指标，总共呢差不多600维的这样的一个评测体系，应该说比较全面的能够衡量一个大模型的这个能力。那这个评测体系是用自动化方式进行的，在线。当然，如果一个模型开源，然后把模型拿来直接这个在实验室评测，没问题。如果一个模型能开放 API， 我们就直接调用，也能评测，速度很快，第2天就出这个全面的评测报告了。如果咱们的刚才说的研发团队希望呢，这个对自己的模型进行评估，也可以采用这个体系呢，来这个自行评估，不去公开指标。有的时候大家在研发，对吧？有的指标好，有的指标不那么好，这没有关系，通过这个测评呢，来不断的这个提升和发展。目前呢，这个天秤的开源大模型评测体系呢，已经面向公众开放注册申请。目前呢，在这个硬件方面支持英伟达、华为的升腾、寒武纪、昆仑芯等多种芯片架构，以及呢 PyTorch、MindSpore 等多种深度学习框架。那此外呢，在这个天秤在我们在 GitHub 上的一个项目中，也分享了，目前主要是语言模型的评测。我们目前呢也增加了多模态文图生成的评测工具，当然文图生成的这一块还在开发中，欢迎大家呢使用。今年年初呢，同样是在这个科技部的大模型的这样的一个旗舰项目支持下，正式发布了 Flag Open 大模型技术开源体系。我刚才尽管在介绍这个智源的大模型的这个最新的进展，但是我一直在说我们是在做开源的模型，这个模型没有任何保留的给全社会开放。那么这个大模型的这样的一个旗舰项目呢，实际上目前也有8个团队在国家项目的支持下呢，在开展研究。那么他们的一些优秀的算法，后续也会通过这个评测集成的方式，变成一个体系。大模型不是任何一家机构或者一家公司垄断的技术，大模型技术体系是大家共建共享。我们要共建一个治理社会所需要的一套基础的算法体系。那么这样的一个 Flag Open 的大模型的技术开源体系呢，希望在推动、在加强合作方面，能够做出基础性的贡献。 目前的 FlagOpen 中的这个 AI 算法方面，已经把我刚才讲到的所有的开源模型以及国内外的一些模型和背后的算法集成进来了，支持并行加速技术 FSDP， 集成了高效推理技术 LoRa 和 BM-Inf。所以呢，在这样的一个开源的这个体系下面，如果一个机构，即便你是从零开始要做大模型，你也可以用这样的一套体系，很快的呢开展自己的这个技术研发活动。那么其中的 FlagPerf 是关于硬件评测的，我们过去这个1年在这方面做了很多工作，也有可以说是很精确的对硬件的性能的评测的结果。目的呢还是为了促进咱们芯片这个硬件的发展。我们掌握的情况，我们的芯片发展很快，所以我们也对这个基础软件体系更好的支撑 AI 的发展呢，这个抱有充分的信心。这个天秤这样的一个大模型的评测平台呢，开源了，刚才说已经开源了多模态的评测工具，但是这个呢还需要进一步的发展。在 Flag Data 就是数据的处理方面，也这个发布了一系列的数据分析的、清洗的和微调的这样的工具。那这些工具呢，本身我们自己就在用，但是我们也把它拿出来供大家。如果你做数据加工清洗的话，你也可以去使用这样的工具，来开发这个自己的数据清洗系统。那么还有一个呢，就是大家关心的大模型的生态中最重要的，可以说物理基础，其实仍然是要回到软硬件。那么在 AI 的时代，软硬件应该是什么样的一种形态呢？我们都知道啊，我们经过了2个时代，一个呢就是 PC 互联网时代，在那个时代，最初呢是 Intel 这样的一个体系，在主导着整个的生态。那么后来呢，出现了 Linux， 现在 Linux 操作系统呢也已经成为这个操作系统的这个主要的一个平台。在移动互联网时代呢，出现了2个生态，一个呢是这个 iOS 的封闭生态，苹果在这个优化；另外一个呢是安卓加 ARM 的生态，这个是通常大家知道准封闭半开放生态。安卓呢是开源的，但是呢也是这个受到一定的这个管控的，不像 Linux 那样那么开放。那么在 CPU 方面，刚才讲 RISC-V 在这样的一个时代呢就出现了，而且呢现在在 CPU 的这样的一个领域已经应该说正在发挥主导作用。所以在智能时代这样的一个基础软件体应该是什么样的？我们认为，当然也不仅仅是我们认为，应该全世界应该主要的这个观点都是它一定是一个开源开放的时代。那么今天尽管这个大模型在很多系统方面表现已经很好，但是如果让全人类用，让千家万户用，让千千万万的企业去用的话，一个封闭的生态是不会这么长远发展下去的。一个开源的生态，在软件上要开源，在硬件上要开放，大家既要竞争又要合作，这是一个这个千千万万的企业共同竞争、共同合作营造出来的开源开放的生态体系。在这方面呢，我们国家应该说已经这个做了很多的努力，很多企业、很多机构做的这个技术和模型都是开放的，但是呢，我们还需要加强。我们初步统计了一下今年以来的语言模型的开源的这个大模型开源的这个项目，全世界范围之内呢，开源的总共有42项。我们国家呢，这个放出来的啊，所谓放出来的就是我有，但是呢有38项，其中9项是开源的。那相比之下，我认为我们的开源开放力度还是远远不够的。我们应该这个进一步加强开源开放。开源开放也是竞争，你真有水平、真有好算法拿出来，大家去评测、去比、去继承，才证明技术水平，而不是这个我就仅仅靠这样的一个结果来说这个是不是优秀。在语言的这个数据方面，我们也做了一个工作，也是目前应该说大家急需的一个大规模的可商用的中文开源的指令数据集。我相信很多做大模型的这个机构或者是企业都在做这个同样的事情。 这是这个对齐、调优必须的一个能力。那个 CYG 呢，应该说目前是全世界范围之内这个规模最大的一个中文的开源的指令集。一期呢，第一期有171K 的开源可商用的中文指令数据已经这个开放了，已经有很多下载，大家已经在用了。我们呢还在开发第2期，争取成为规模最大，而且是持续更新的中文的多任务的指令的数据集。那么讲了大模型，我刚才讲还有2条技术路线。尽管我们花了80%的这个人力物力资源在做大模型，但是另外2条路线也不能不做，也必须做。虽然它更漫长一点，但是那是这个通往这个 AGI 的另外2条路径。第一个呢，就是在具身的多模态交互模型方面，我们探索在 Minecraft 的虚拟世界中，让智能体学习完成各种由语言描述的任务，比如告诉智能体制作一个石锤子，建造一个木质的避难所，告诉它这样的一个任务，它就可以自己在游戏世界自己完成了，不要再用鼠标啊、控制啊一步步的走，这些东西都不要了。你要想干啥，你告诉它就可以。这个呢，应该说是通用人工智能的一个新的赛道。那么全世界范围之内呢，也有不少机构在进行。我们呢，从去年基于模仿学习的策略大模型 VPT 奖励函数 MineClip， 到今年利用大规模语言模型进行任务分解和规划的Plan for MC 这样的一个模型方面，完成了大量的任务。我记得2个月之前发布这个模型的时候，24项任务应该是全球范围之内完成任务最多的这样的一个智能模型。原来的那个就是现有的这些方法呢，是依赖人类的知识和这个提示的。下一个目标呢，我们是让智能体在这个基础上，在开放世界持续学习。所以包括策略集和专门的针对这种多模态交互的大模型方面呢，进一步的研究，从而呢让它自适应的在开放世界中能够完成更多的任务，并且具备自己的创造性的完成任务。在类脑智能和生命模拟这个方向，我们的工作也在继续。去年呢，智源大会发布了最高精度的仿真线虫，到现在为止，这仍然是精度最高的。那个论文呢，还正在评审过程中。有了这个工作基础，我们把这个仿真这个线虫所用的生命模拟平台叫 Evaluation 天眼全面开源，并提供了在线服务。所以大家如果想做同样的任务，你可以拿这个代码自己去这个运行去做。你也可以，你说我没有那么多计算机算力，我只有一些生物数据，那没关系，你通过在线的方式可以这个在我们的这个平台上完成。天眼平台呢，有4项最显著的特点。第一个是当今效率最高的精细神经系统仿真的平台。第二呢，支持超大规模的神经网络仿真，目前呢已经高效地复现了领域内多个大规模的神经模型。第3个呢，我们是提供在线工具，刚才讲的一站式的，你只要有生物数据，那就可以一站式的建模、仿真、可视化，在一个平台上可以完成。而且其中这个可视化的交互是天眼独有的，整个你可以观察神经系统在这样的一个运行过程中，它的信号发生了什么样的变化，是怎么样？因为我们最终想知道生命智能背后的每一步，不像今天是黑箱，我们想知道这个到底发生了什么，所有的细节呢，在这个平台上呢都可以看到。我们针对呢目前就是神经科学领域结构和功能最完整的一个模型呢，是美国艾伦研究所的 V1， 也就是初级视觉皮层的一个模型。我们呢在这个天眼平台上，从仿真速度和模型细节2方面入手，提供了一个在它的基础上提升了一个运行更快、更加符合生物 生理约束的一个新版本。那么特别的呢，我们可以对千万规模的精细神经元的这样神经网络进行高效的可视化，以及呢10万舱室规模的交互。所以就像刚才说的，你可以像神经系统是一个复杂的森林，今天还是一个黑暗森林，你可以在这个森林中对你周边一定范围之内的这个树木、树枝、树叶所有的细节看清楚，到底在点亮之后就可以看清楚到底在发生什么。我们相信呢，这个一定会无论是对于这个神经科学，还是对于人工智能研究呢，都能起到基础性的支撑作用。为了加快这个计算速度，我们和天津超算合作，把这个天眼呢已经在天河超级计算机上成功的部署，在节省能耗的情况下，提升了20倍的这个计算速度，可以说实现了全球范围内最极致的这个神经系统仿真的性能。第一次把大规模精细神经系统的仿真速度逼近生物真实。现在这个工作还在做，未来呢，我们还跟天河，就是天津的超算的进一步合作，进一步挖掘我们超算的这个硬件和软件的潜力，早日实现全球第一个精细的人类大脑。当然，这个时间我说早日啊，应该是早年，可能还得15到20年的时间才能做到。但是这是通向刚才讲的 AGI 的一个必须的这么一个里程碑。那下面呢，就请大家看一下现在这个神经系统的一个模型。这就是智能在发生的一个物理的生理的基础。我刚才讲的这个神经系统，这其实是智能的一个最直接的一层。再往下就是我们的这个细胞、蛋白质这样的有机分子。这一块呢，我们的健康计算中心，专注于运用通用人工智能和大模型的这些前沿技术，不断的开拓生命科学，包括服务于健康这样的研究的边界。主要的呢是蛋白质的设计和量子化学这2个方向。在2023年，研究中心研发的 Open Complex 大分子预测模型，在 Camel 蛋白质结构预测竞赛中赢得了年度冠军，不是一次冠军，是连续的，每次比赛都是冠军。其中有一次我们忘记了提交数据，剩下的只要提交数据的全部是这个冠军。目前呢，这个中心呢正致力于开发基于结构的大分子，包括蛋白质，包括核酸适配体，的生成模型，并且呢把它应用于药物设计等领域。那此外呢，还正在构建一个生物分子的统一的大模型，希望呢能够推动包括人工智能、包括生命科学、包括医药设计这样的各类任务的发展。那最后呢，我就简单的这个报告一下今年这个志愿大会的安排。志愿大会呢，今年是第5届，我们一直在努力，我们追求的呢是国际视野、技术前沿、思想碰撞、洞见未来，办成最受人工智能精英人群喜欢的专业的大会。应该说，1年1度的志愿大会已经成为北京、全国乃至全球范围之内的一个独具特色的一个专业的盛会，成为北京科技创新中心建设的一张闪亮的名片。像往年一样，今年的志愿大会同样是群星灿烂，汇聚了人工智能领域最关键的人物、最重要的机构、最核心的话题和最内行的观众。我们这个大会呢，如果大家要去比的话，就是全球范围之内，能够有这么多这个顶尖专业人士这个出席的，至少是极其罕见。那么马上呢，我这个报告还有1分半钟结束之后，我们就会进入今年的这个 keynotes。 那么今年呢，我们有2位嘉宾，一位呢是图灵奖的获得者，深度学习的3巨头之一杨乐坤。乐坤呢现在在法国，凌晨4点。原来他是在美国答应的这件事儿，但是呢，法国政府有活动，他必须去法国。然后我说：“那你太辛苦了，4点钟要接入，你拍个视频吧也行。”他说：“不，我就要实时的跟大家这个讲。”所以大概1分钟之后啊，我们就接入。那么我们上午的第2位嘉宾呢 ，Max Tegmark， 他已经在前台就座了。等会儿呢，他会分享他的观点。这2位嘉宾呢，他观点是有一定的对立的。乐坤认为，我们应该乐观的发展通用人工智能，现在远远没有到这个应该紧张的时候。Tegmark说，现在就要加强管理和控制。等会儿我们听他们的精彩的观点。当然，安全、伦理、风险，这肯定是我们应该关注的高度关注的话题。明天呢，明天一天全天的一个关于 AI 安全的论坛，有很多著名的专家。这里边呢包括UC Berkeley 的著名的人工智能教授，也是可以说几千万人都是读着他的书学的 AI。Russell 教授，他也已经在现场，这会儿不在现场，他明天会现场跟大家进行交流。还有呢，我们的深度学习的教父 Jeffrey Hinton， 老先生身体不好，本来前年答应来讲，在最后大会要开的前2天，突然给我们发个邮件说，不行，我发现我的方法里边有个 bug， 这个会不能讲了。我说那不行啊，那我们都已经宣传出去了。Hinton 说没关系，我马上在推特上发一部消息，就说我是有 bug， 所以不能讲。后边的相关的报告都不讲了，这一周安排的报告都不讲了。但是今年呢，大家也都新闻上都看了很多报道啊，他呢也是实时接入。明天呢会在伦敦给大家讲他对人工智能最新的担心和他的我觉得这是很难得。当然，还有一位难得的人物，就是大家关注度很高的 OpenAI 的 CEO Sam Altman， 也是明天实时呢在线跟大家进行在这个论坛上跟大家进行交流。那这次会呢，我们差不多跟往年是类似的规模，有20个论坛，100场报告，顶尖的专家、顶尖的观众，让我们呢共同来享受这2天的纯粹的、专业的 AI 的最新的思想、最新的进展。谢谢大家。
谢谢铁军。接下来我们进入大会的正式的主题演讲环节。刚才铁军已经提到，这会儿是巴黎时间早晨4点钟。我们有请2018年图灵奖得主 Meta 的首席 AI 科学家、纽约州立大学教授杨立坤博士。Hey, good morning. Good morning, Yang.
Good morning.
It is really a great honor and a privilege to have Professor Yang LeCun to speak at this BAI conference. Professor LeCun is a renowned computer scientist, best known for his groundbreaking work in the field of AI, especially in deep learning and convolutional network. So when we talk about CNN, in this field in AI, we're not referring to the TV station, but we're referring to Yang LeCun's work, convolutional neural net. He is often regarded as one of the founding fathers of modern deep learning technology, having made a pioneering contribution that continue to shape the landscape of AI research and innovations. Professor LeCun has been the recipient of numerous prestigious awards and honors throughout his career. Most notably, in 2018, he received the Turing Award, what we call the Nobel Prize in computer science. Today, Professor Lacombe will give a speech entitled "Toward the Machines That Can Learn, Reason, and Plan." Let's welcome Professor Lacombe. Yang, the floor is yours. Thank you.
All right, thank you very much for the introduction. I hope you can hear me fine. I'm really sorry I can't be there in person. Haven't been to China in a very long time. So I'm going to talk a little bit about the future of AI, the way I see it, and to essentially bridge the gap between what we observe in the capacity of humans and animals and the type of artificial intelligence we're capable of producing today. And what's missing is the capacity to not just learn, but also reason and plan in AI systems. So a lot of what I'm going to talk about is either kind of a direction, if you want, where I think AI research should go in the next decade or so, as well as some preliminary results, but no complete systems. So the first thing I should say in sort of colloquial English is that machine learning is not particularly good compared to humans and animals. For a few decades now, we've been using supervised learning, which requires too many labels. Reinforcement learning works well, but requires an insane amount of trials to learn anything. And of course, in recent years, we've been using a lot of self-supervised learning. But the result is that those systems are somewhat specialized and brittle. They make stupid mistakes. They don't really reason or plan. They sort of react really quickly. And when we compare with animals and humans, animals and humans can learn new tasks extremely quickly and understand how the world works and can reason and plan. And they have some level of common sense that machines still don't have. And that's a problem that was identified in the early days of AI. That's partly due to the fact that current machine learning systems have essentially a constant number of computational steps between input and output. That's why they really can't reason and plan to the same extent as humans and some animals. So how do we get machines to understand how the world works and predict the consequences of their actions like animals and humans can do, can perform chains of reasoning with unlimited number of steps, or can plan complex tasks by decomposing them into sequences of subtasks? That's the question I'm going to ask. But before I say this, I'll talk a bit about self-supervised learning and the fact that it really has taken over the world of machine learning over the last several years. This I've been advocating for quite a number of years, 7 or 8, and it's really happened. A lot of the results and the successes of machine learning that we see today are due to self-supervised learning, particularly in the context of natural language processing and text understanding and generation. So what is self-supervised learning? Self-supervised learning is the idea of capturing dependencies in an input. So we're not trying to map an input to an output. We're just being provided with an input. And in the most common paradigm, we mask a part of the input and we feed it to a machine learning system. And then we reveal the rest of the input and then train the system to capture the dependency between the part that we see and the part that we don't yet see. Sometimes it is done by predicting the part that is missing, and sometimes not entirely predicting, and that's well explained in a few minutes. So that's the idea of self-supervised learning. It's called self-supervised because we essentially use supervised learning methods, but we apply them to the input itself as opposed to kind of mapping to a separate output that is provided by humans. So the example I show here is a video prediction where you show a short segment of video to a system and then you train it to predict what's going to happen next in the video. But it's not just predicting the future, it could be predicting kind of data in the middle. So this type of method has been astonishingly successful in the context of natural language processing, and all the success that we've seen recently in large language models are a version of this idea, right? So the basic principle here is that you take an input, a text, let's say a window over a piece of text, and by removing some of the words, replacing them by a blank marker. And then you system runs a represent text, and the astonishing thing is that it can do this which is for a subsequent task.
各位来宾，不好意思，看来法国的WiFi 的服务还是不太可靠啊，尤其是在这个旅馆里面的WiFi。我们给他几秒钟，看他再重新上线啊。他现在重新连一下。所以我们虽然在这个 AI 的这个时代啊，我们这个在互联网的问题技术问题还是没有得到彻底的解决。对，我们正在重新连线。
好，我们很快，这个那空教授又上线了，OK。好，同意。
My apology. It
Okay,
turns out
here we
my
go.
computer has a hardware problem and just crashed. So I had to reboot. I hope this is going to take us to the end. Okay, so I was saying this self-supervised learning technique consists in taking a piece of text, removing some of the words in that text, and then training a very large neural net to predict the words that are missing. And in the process of doing so, the neural net learns a good internal representation that can be used for a number of subsequent supervised tasks like translation or text classification or things of that type. So that's been incredibly successful. And what's been successful also is generative AI systems for producing images, videos, or text. And in the case of text, those systems are autoregressive. So the way they're trained using self-supervised learning is by not predicting random missing words, but by predicting only the last word, right? So you take a sequence of words, suppress the last word, and then train a system to predict the last word, the last token. They're not necessarily words, but subword units. And once the system has been trained on enormous amounts of data, you can use what's called autoregressive prediction, which consists in predicting the next token, then shifting that token into the input, and then predicting the next token, and then shifting that into the input, and then repeating the process. So that's autoregressive LLMs, and this is what the popular models that we've seen over the last few months or years do. Some of them from my colleagues at Meta, at FAIR, Blunderbot, Galactica, and Llama, which is open source. Alpaca from Stanford, which is a refinement on top of Llama. Lambda, Bard from Google, Chinchilla from DeepMind, and of course ChatGPT and GPT-4 from OpenAI. The performance of the systems is amazing if you train them on something like a trillion token or 2 trillion tokens. But in the end, they make very stupid mistakes. They make factual errors, logical errors, inconsistencies. They have limited reasoning abilities, produce toxic content, and they have no knowledge of the underlying reality because they are purely trained on text. And what that means is a large proportion of human knowledge is completely inaccessible to them. And they can't really plan their answer. There's a lot of studies about this. However, those systems are amazingly good for as writing aids, as well as for generating code, for helping programmers writing code. So you can ask them various things to write code in various languages, and it works pretty well. It gives you a good start. You can ask them to generate text, but again, they can elucidate or confabulate stories. So this is a joke that my colleague played on me. They said, "Did you know that Yannick dropped a rap album last year? We listened to it, and here is what we thought." And the system comes up with some story that somehow I produced a rap album, which of course is not true. But if you ask it to do it, it will do it. So that's entertaining, certainly, but that makes the system not so good for as information retrieval systems or as search engines, or just if you just want factual information. So again, they're good for writing assistants, first draft generation, stylistic polishing, particularly if you're not a native speaker in the language that you're writing. They're not good for producing factual and consistent answers, taking into account recent information because they have to be retrained for that. They mimic behavior in the training set, and that is no guarantee that they will behave properly. And then there is issues like reasoning planning, doing arithmetics and things like this, for which they would use to have tools such as search engines calculator, database queries. So that's a really hot topic of research at the moment, of how to essentially get those systems to call tools. This is called This is called extended language model. And I co-authored a review paper on this topic with some of my colleagues at FAIR on the various techniques that have been proposed for extended language models. We're easily fooled by their fluency into thinking that they are intelligent, but they really are not that intelligent. They're very good at retrieving memories approximately. But again, they don't have any understanding of how the world works. And then there is kind of a major flaw, which is due to the autoregressive generation. If we imagine that the set of all possible answers, so the sequences of tokens, is a tree, if you want, here represented by a circle, but it's really a tree of all the possible sequences of tokens. Within this enormous tree, there's a small subtree that corresponds to the correct answers to the prompt that was given. And so if we imagine that there is an average probability E that any produced tokens takes us outside of that set of correct answers, and the errors that are produced are independent, then the probability that the answer of length n is correct is 1 minus e to the power n. And what that means is that there is an exponentially diverging process that will take us out of the tree of correct answers. And this is due to the autoregressive prediction process. There's no way to fix this other than making e as small as possible. And so we have to kind of redesign the system in such a way that it doesn't do that. And in fact, other people have pointed the limitations of some of those systems. So I co-wrote a paper, which is actually a philosophy paper with my colleague Jacob Browning, who is a philosopher, about the limits of training AI systems using language only. The fact that those systems have no experience of the physical world, and that makes them very limited. There's a number of papers either by cognitive scientists, such as the one on the left here from MIT group, that basically says, the kind of intelligence that the system has is very restricted compared to what we observe in humans and animals. And there are other papers by people who come from sort of more classical AI, if you want, sort of not machine learning based, that try to analyze the planning ability of those systems and basically conclude that those systems cannot really plan, at least not in ways that are similar to what people were doing with sort of more classical AI search and planning. So how is it that humans and animals can learn so quickly? And what we see is that babies learn an enormous amount of background knowledge about how the world works in the first few months of life. They learn very basic concepts like object permanence, the fact that the world is three-dimensional, the difference between animate and inanimate objects, the notion of stability, the learning of natural categories, and the learning of very basic things like gravity, the fact that when an object is not supported, it's going to fall. Babies learn this around the age of 9 months, according to this chart that was put together by my colleague Emmanuel Dupoux. So if you show a 5-month-old baby, the scenario here at the bottom left, where a little car is on a platform and you push the car off the platform and it appears to float in the air, 5-month-old baby are not surprised, but 10-month-old baby will be extremely surprised and look at the scene like the little girl at the bottom here, because in the meantime they've learned that objects are not supposed to stay in the air; they're supposed to fall under gravity. And so those basic concepts are learned in the first few months of life. And I think what we should reproduce with machines is this ability to learn how the world works by watching the world go by or experiencing the world. So how is it that any teenager can learn to drive a car in 20 hours of practice, and we still don't have completely reliable level 5 autonomous driving, at least not without having extensive engineering and mapping and LiDARs and all kinds of sensors, right? So obviously we're missing something big. How is it that we have systems that are fluent, that can pass the law exams or medical exams, but we don't have domestic robots that can clear up the dinner table and fill up the dishwasher, right? This is something that any 10-year-old can learn in minutes. And we still don't have machines that can come anywhere close to doing this. So, we're obviously missing something extremely major in the AI systems that we currently have. we're nowhere near reaching human-level intelligence. So how are we going to do this? And in fact, I've kind of identified three major challenges for AI over the next few years: learning representations and predictive models of the world, of course, using self-supervised learning, learning to reason. So this corresponds to the idea from psychology, from Daniel Kahneman, for example, of system 2 versus system 1. So system 1 is the kind of human action or behavior that corresponds to sort of subconscious computation, things that you do without thinking about them. And then system 2 are things that you do deliberately, consciously. You use the full power of your mind. And current AI systems basically only do system 1 and not very good at all. And then the last thing is learning to plan complex action sequences hierarchically by sort of decomposing complex tasks into simpler ones. So I wrote a vision paper about a year ago that I put up on Open Review that you're invited to look at, which is basically my proposal for where I think AI research should go over the next 10 years. The title is A Path Towards Autonomous Machine Intelligence, and which is sort of a written version of the talk you're hearing right now, if you want. It's based around this idea that we can organize a variety of modules into what's called a cognitive architecture. And within this system I'm proposing, the centerpiece is the world model. So the world model is something that the system can use to basically imagine a scenario, imagine what's going to happen, perhaps as a consequence of its act. So the purpose of the entire system is to figure out a sequence of actions that, according to its own prediction, using its world model, is going to minimize a series of costs. So the costs, you can think of them as measuring the level of discomfort of this agent. And by the way, many of those modules have corresponding subsystems in the brain. The cost module is in the basal ganglia, the world model, the prefrontal cortex, short-term memory would be the hippocampus, the actor could be the prefrontal cortex, and of course the perception system is the back of the brain where all the perception is analysis of sensors is performed. So the way this system operates is that it perceives the state of the world, combines that with its sort of previous idea of the state of the world that may be stored in a memory, and then uses the world model to predict what would happen if the world just evolves, or what would happen as a consequence of actions that the agent would take, which is inside of this yellow actor module. So the actor module proposes a sequence of actions. The world model simulates the worlds and figures out what's going to happen as a consequence of those actions. And then a cost is computed. And then what's going to happen is the system is going to optimize the sequence of actions so as to minimize the world model. So what I should say is that whenever you see an arrow here going one way, you also have gradients going backwards. So I'm assuming that all of those modules are differentiable, and we can do this inference of the sequence of actions by backpropagating gradients so as to minimize the cost. So this is not minimizing with respect to parameters, which would be for learning. This is minimizing with respect to latent variables, and this is taking place at inference time. So there's really two ways to use that system. It's akin to system 1, which I call mode 1 here, where basically it's very reactive. So you observe the state of the world, run it through a perception encoder, which gives you an idea of the state of the world, and then run this directly through a policy network in the actor that just directly produces an action. So there's no need for a world model here. It's just a reactive policy. Then mode 2 is one in which you observe the world and extract a representation of the state of the world, S0, and then you imagine, the system imagines a sequence of actions, from A0 to a large T, and then using its world model imagines the result, the effect of taking those actions. those predicted states are fed to a cost function. And the entire purpose of the system is basically to figure out a sequence of actions that will minimize the cost according to the prediction. So this world model here that is repeatedly applied at every time step essentially predicts a representation of the state of the world at time t+1 from a representation of the world at time t and an imagined proposed action. This idea is very much similar to what people in optimal control call model predictive control. And there's a number of models that have been proposed in the context of deep learning that use this idea for planning trajectory, work by my student Michael Enaf and myself, and Alfredo Conziani at ICLR 2019, a series of work by Danijar Hafner, Dreamer, V1, V2, etc., and other work from Berkeley and various other places. So the question here is how do we learn this world model, essentially? Let me skip this. What we're expecting to do is some more complicated version of this, where we have a hierarchical system that extracts through a sequence of encoders, extract more and more abstract representations of the state of the world, and use different levels of world models of predictors to predict the state of the world at different levels of abstraction and make prediction at different time scales. So at a higher level here, for example, if I want to go from New York to Beijing, the first thing I need to do is go to the airport and then catch a plane to Beijing. Okay, so that would be sort of a high-level representation of the plan. The ultimate cost function could represent my distance from Beijing, for example. And then the first action would be go to the airport, and my state would be, am I at the airport? And then the second action would be catch a plane to Beijing. Now, how do I go to the airport from, let's say, my office in New York? Well, the first thing I need to do is go down to the street and catch a taxi and tell it to go to the airport. And then how do I get down on the street? I have to stand up from my chair, go to the exit, open the door, go on the street, etc. And then you can imagine decomposing this task all the way down to the millisecond by millisecond muscle control that you need to do to accomplish this task. So all complex tasks are accomplished hierarchically in this way. And this is a big problem that we don't know how to solve with machine learning today. So this architecture that I'm showing here, no one has built it yet. No one has proved that you can make it work. So I think that's a big challenge, hierarchical planning. The cost function can be composed of two sets of costs modules, and would be modulated by the system to decide what task to accomplish at any one time. So there are two submodules in the cost, some that are sort of intrinsic costs that are hardwired and immutable. And you can imagine that those cost functions will implement safety guardrails to ensure that the system behaves properly and is not dangerous, is not toxic, etc. And so that's a huge advantage of those architectures, which is that you can put costs that are optimized at inference time. And so you can guarantee that those criteria, those objectives will be enforced and will be satisfied by the system's outputs. So this is very different from autoregressive LLMs where there is no way basically to ensure that their output is good and non-toxic and safe. Here, it's possible because it's possible to impose this because that's basically hardwired into the system that it needs to optimize those cost functions. And then there might be other cost functions, perhaps trainable, that model the satisfaction of the task that is being accomplished, and those could be trained. Those are similar to critics that are used in reinforcement learning. I'm assuming that all of those modules are differentiable. So how are we going to build this and train this world model? So again, we're going to do something like in this little example here, kind of capture the dependency in video, perhaps predict the a segment of a video, a future segment of video from the present and the past. And if you train a neural net to just predict videos, it doesn't work very well. You get very blurry predictions. This is old work here at the top from 2016, where we attempted to do video prediction. And what you get are blurry prediction because the system cannot predict in advance what is going to happen in the video. So it predicts an average of all outcomes. And that ends up being a blurry prediction. There's a similar scenario here at the bottom where this is a stylized picture from a top-down camera looking at a highway and following the blue car. And the predicted frames from this video prediction system are blurry, again, because the system doesn't know exactly what's going to happen. And so it predicts an average, and that's a bad prediction. So the solution I'm going to propose to basically deal with this issue of multimodality is what's called a joint embedding predictive architecture. And so let me explain a little bit what this is. So we have generative architectures, things like autoencoders, variational autoencoders, maxed autoencoders, or the type of large language models I was talking about earlier. And there, what you do is you have an observed variable X, an encoder, a predictor or a decoder that produces a prediction for the variable you want to predict, Y, and then you measure the divergence of some kind, some distance between the predicted Y and the observed Y. And there's a flaw with this, and the flaw is that the systems have to predict every single details about Y. So this is not too much of a problem when you're predicting words, because you can represent a distribution over words using a softmax, a long vector of probabilities of numbers between 0 and 1 that are normalized. So it's easy when Y is a discrete variable. But when Y is a continuous variable, like a video frame, for example, or a set of video frames, predicting all the details in that video frame is essentially impossible. And most of the details are not even useful to capture. So for this, I propose the architecture on the right, which is called a joint embedding architecture, or in this case, joint embedding predictive architecture. And basically, both X and Y are fed through encoders. And the prediction takes place not in the input space, but in representation space, so that there's a predictor network that tries to predict the representation of Y, SY, from the representation of X, SX. A simple form of this joint embedding architecture is something that I proposed many years ago in the early 90s called Siamese network. And those kind of architectures have become somewhat popular over the last few years for self-supervised learning in the context of images. So there are basically no method today, no generative architectures today that work properly to learn features for vision. With one exception, which is a masked autoencoder from my colleagues at FAIR, including Kai-Ming He. But it doesn't work very well in the sense that the features that are produced are not very good. You need to fine-tune the system to get good results. So if you want features that are good without fine-tuning, the generative methods are really not good. You need to use the joint embedding architectures. So there's a number of methods like Pearl and Moko, SimClear, Barlow Twins, and VicReg that essentially use this joint embedding architecture, and they do work very well for self-supervised learning and produce extremely good features. Another method that is not listed here is Dino, which is a method by my colleague at FAIR in Paris. A slightly more sophisticated version includes a predictor that tries to predict the representation of Y from that of X, as opposed to just trying to make them equal. But that would be deterministic prediction. On the right is a version of that system in which the predictor takes as input a latent variable, and that latent variable can be used to parameterize a set of possible predictions of SY and basically make non-deterministic predictions. So you would have a system of this type where if you want to use this architecture to build a world model, the predictor would take two variables, a set of latent variables that represent everything you don't know about the world, all the unobserved variables that represent the state of the world that would allow you to predict what's going to happen next. And then another set of variables that would represent an action you might take, right? So from an observation of the state of the world X, you extract a representation of it, then given an action, and through maybe sampling a set of latent variable, you can make one prediction about the representation of the state of Y, and that Y variable can be run through an encoder. So the next question is, how do we train this system? And that system might include other criteria represented at the top right, like C of S, that may represent constraints that we want the system to satisfy, or cost functions that indicate what type of information we want the system to learn to extract. So before I talk about how we train this, I have to talk a little bit about what's called energy-based models, which is the framework through which we can understand this, because we can't understand those systems through the traditional methods of probabilistic modeling, unfortunately. So what is an energy-based model? Energy-based model is a function, an energy function, that captures the dependency between, let's say, two sets of variable X and Y. And the way it does this is by putting a scalar output, where that scalar output is small, takes low values when X and Y are compatible with each other. So for example, Y is a good continuation for the video clip X. And then it takes higher values outside of whenever Y is not compatible with X. So it's symbolized here in this the diagram on the right, where let's say X and Y are scalar variables, and the set of data points that you've observed are those black dots. So you want the energy function, of course, which is going to be parameterized through a neural net and trained. You want this energy function to take low values around the data points, and then higher values outside. And so basically, you can think of this as an implicit function that represents the dependency between X and Y. Through learning, it's really easy to train this energy function to give low energy for the data points you train it on, but it's harder to figure out how to make sure that the energy is higher outside of the training samples. So there are two classes of methods to do so. One is called contrastive methods, and it consists in generating contrastive points, those green flashing dots here, outside of the manifold of data, and then pushing their energy up, right? So you simultaneously push the energy down of the data points that you have, and then you generate contrastive data points, which must be hallucinated if you want. You push their energy up. And so by pushing down and pushing up on the right place, the energy surface will take the right shape. But my preference goes to something called regularized methods, and they work by essentially imposing a regularizer on the energy function so that the volume of space that can take low energy is limited or minimized. So whenever you push down on the energy of some region, the other regions have to go up because there is only a limited volume that can take low energy. So that's those two categories. I think there is a major limitation with contrastive methods, which is that as the space of Y increases in dimension, the number of contrastive points you need to generate for the energy function to take the right shape grows exponentially with the dimension. And I think that's a flaw. Whereas regularized methods tend to be more efficient by basically minimizing the volume of space that can take low energy. So how we so basically, I'm asking you to accept four things. The first thing is to abandon generative models. Okay, this is not very popular at the moment because generative models are all the rage. Everybody is talking about them. What I'm saying is that if you want to have a system that can learn world models, it cannot do this by just being trained to produce video frames, for example, because it's too complicated to make predictions in high-dimensional continuous spaces. So we have to use those joint embedding architectures, which means we have to abandon the idea that we're going to have generative models. For text, it's fine, but not for video. We have to abandon the idea of using probabilistic modeling and use those energy-based framework. The reason being that you cannot, if you're going to run Y through an encoder, you cannot invert this encoder function to produce a conditional probability P of Y given X. This is not possible in this context. you have to abandon the idea that you're going to model a distribution. You're just going to compute this energy function, which is a proxy, a simpler proxy for something like a distribution. I'm also telling you to abandon contrastive methods in favor of those regularized methods. And of course, for many years now, I've said that if reinforcement learning should be minimized, we should minimize the use of reinforcement learning because it's extremely inefficient. So basically use planning whenever we can and only use reinforcement learning where we have no choice. So what are those regularized methods for joint embedding? And this is really kind of the core of the talk, if you want, the interesting part. Okay, so here's the problem. We're going to have a collapse issue, which is that if we just train one of those joint embedding predictive architecture to minimize the prediction error, which is the error you make of predicting the representation of y from the representation of x, it's not going to work. The system is basically going to collapse because it's going to ignore x and y, produce sx and xy vectors that are constant, so that the prediction error is 0. And that model is not going to capture the dependency between x and y because it's going to give you 0 energy for everything, right? You will have succeeded in making the energy low on your training samples, but the energy will be 0 everywhere. So you have to prevent this collapse from happening. And the technique that I'm proposing here is to essentially have some measure of the information content of Sx and the information content of Sy and maximize them. Okay, so find a way of maximizing the information content of both Sx and Xy, and that will prevent this collapse. And in fact, this has the regularization effect I was telling you earlier, basically minimizing the volume of space that can take low energy. If you have a latent variable for the predictor, you also need to regularize the information content of that latent variable, but there you need to minimize the information content. If you have a latent variable that is too informative, you're also going to have a collapsed model that predicts that has 0 energy for any pair xy. So how are we going to maximize the information content of Sx and Xy? So a simple way in which those systems can collapse is by making Sx and Sy constant. You can prevent this from happening by having a cost function at learning time that basically guarantees that the standard deviation of all the components of Sx is above a certain threshold, in this case 1. So this is a hinge loss that pushes the standard deviation of the every component of S to be larger than 1. Okay, so the system cannot put just constant outputs, and this is computed over a batch, if you want, of a few samples. We do the same thing for both Sx and Sy. So this is called variance regularization, and there's a number of papers here at the bottom that have been using this method, coming out of my group from Meta. Barlow twins, which was the first version of this, VCREG, which is a improved version, VCREG-L for image segmentation, and this is similar to a work by Yi Ma at Berkeley. He's actually now in Hong Kong for some time, co-authored with Harry Shum, called NCR squared, which has a very similar idea. So that is not sufficient to prevent the system from collapsing, because the system could choose to make all the components of Sx equal or very correlated. And so what you have to do as well is basically minimize the off-diagonal terms of the covariance matrix of Sx. So you take pairs of coordinates, measure their covariance, and for 2 different coordinates, you try to minimize the covariance term. So basically, the cost function is the square of the covariance term for every pair of variables. So that will decorrelate the variables, and that's still not sufficient. And so what we do is play a trick here. We run Sx through an expander module that produces a larger vector Vx, and then we apply the variance covariance criterion to this larger vector Vx, and this actually has the effect, and we have some papers on this. This will have the effect of making the components of Sx more independent with each other, at least pairwise independent. So this method is called VCREG, and that means variance, invariance, covariance regularization. So variance is this criterion, covariance is that criterion, and then invariance is this prediction criterion. VCREG. We're really happy with that method. It works really well. So we can train one of those joint embedding architectures with pairs of images, which are distorted versions of each other. So it's the same model as I was talking about earlier, where you take an image and you corrupt it. And here, in this case, you transform it in some ways. You train this joint embedding architecture using VCREG, and then you chop off the expander, or the projector in this case, use the representation produced by the system as input to a linear classifier that you train supervised and measure the performance. And this works really well. You can get something like in the mid 70% correct on ImageNet with a very simple architecture. We're using convolutional net architectures. And something like ConvNext and things like that. You can now apply the features to other tasks than ImageNet. This is pre-trained on distorted versions of ImageNet. And it works pretty well, including for segmentation, but not perfectly. So you can improve that system by a very simple predictor that tries to match the location of features into images. This is called VCREG L for local. And that works really well for segmentation. So that system really produces fantastic features for segmentation. I should say that another method that is also a joint embedding architecture by our colleagues at FAIR Paris called Dino, and Dino V2 also produces excellent features for segmentation. And it's very similar in many ways. The collapse prevention is different, and the representations are quantized, but in many ways it's a very similar idea. Let me skip ahead a little bit. So this is a more recent work called ImageJEPA. And so this is one of those joint embedding predictive architectures. And there it's purely based on masking. So we're not doing data augmentation. We're just taking an image, running it through an encoder, producing a representation. And in this case, the encoder is a transformer. So we get a complete representation of the image through the transformer. And then we run a partially masked version of the image through the same transformer. So those two share the weights. So this system produces, weaker partial features. And then we train a predictor to predict the representations produced from the full image from the representations obtained with the partial image. So again, ImageJEPA. This is a recent paper by Mido Asran from FAIR in Montreal in collaboration with some of us. And this works amazingly well. It produces really good features. It's very fast, and it doesn't require any data augmentation, which is a huge advantage. It works much better than, for example, masked autoencoder, which is a generative architecture. And it really doesn't require any data augmentation. It can reach something like 81% on ImageNet, which is similar to what other methods can reach using data augmentation. So this is without using data augmentation, purely using masking, which is pretty amazing. And of course, it works really well for transfer tasks and things like that. So okay, so how are we going to use this? I'm coming to the end of my talk here. We're going to use this to build those JEPA architecture, to build hierarchical world models that will be integrated in this full architecture that will allow systems to plan. And what I'm talking about here is the future, because we haven't built this completely. We have some demos of some subsets, but no real complete system yet. So we can use one of the JEPA architectures to extract low-level representations of the input and make predictions at short term with lots of details. Or what we can do is run through another encoder that is going to extract a higher-level abstract representation and make predictions that are longer term, so further in the future. The low level may involve actions that are real actions in the real world, and the higher level will involve latent variables that may represent high-level actions that do not correspond to real actions. And we could use this system, this architecture, in the context of hierarchical planning that I was describing at the beginning of the talk. So we built some versions of this type of hierarchical architecture for video prediction. We don't think we have a perfect recipe yet, but we have something that seems to learn pretty good features from video. So it basically takes 2 frames from a video, runs them through encoders, and then has some predictor that tries to predict the representation of the lower frame from the representation of the first frame, but it does this hierarchically, and simultaneously the same encoder is used to and trained from images using the VCRAG criterion I was talking about earlier. Both of them use VCRAG regularization at every level. So I'm not going to describe the details of this architecture, but basically it's a large convolutional net, and the predictors have a particular structure that basically force the representations to follow some sort of geometric warping, and the warp vector fields are predicted from top to bottom, and basically that system spontaneously, using self-supervised learning, learns the distortion between 2 successive frames in a video and learns to extract representation that represent all the information. If you train that simultaneously with a sort of global image recognition criterion, you get systems in the end that can estimate flow, optical flow, but also can extract representations that can be used for object recognition and segmentation. And we have really good results, which I'm not going to bore you with, but of a system that can simultaneously perform a good flow estimation, object recognition, and object segmentation, and object tracking as well, using completely self-supervised learning. So I'm going to the end. So if we are successful in making systems of this type that are completely general, we're going to be able to integrate them into systems that can predict what's going to happen as a consequence of actions or latent variables, and then use those systems to make to do planning. And to some extent, planning through energy minimization can be seen as a very general framework for reasoning. Reasoning can always be sort of formulated in terms of minimizing some energy function, and so this is much more sort of qualitatively more powerful than autoregressive generation. So steps towards AI systems: self-supervised learning, handling uncertainty in prediction using those JPA architectures and energy-based framework, learning world models from observation using SSL, and reasoning and planning by using energy minimization with respect to action variables. And so this is a kind of reasoning that does not involve any symbols or any logic. It's basically just continuous optimization with vectors. Okay, is there a chance that this kind of architecture will lead us towards human-level intelligence? Perhaps. We don't know yet because we haven't built it, and it's probably going to take quite a long time before we make it work completely. So it's not going to happen tomorrow, but there's good hope that this will take us a little closer, perhaps, to human-level intelligence, where systems can reason and plan. An interesting tidbit about this is that those systems will necessarily have emotions, because the ability to predict an outcome, whether an outcome is going to be good or bad, which is basically implemented by the cost module, is kind of very similar to emotions in animals, right? Fear is caused by an anticipation of a potentially negative result, and elation is produced by the prediction of a very positive result and things like that, right? So systems that are driven by objectives like this, I actually call this objective-driven AI, will have things like emotion, they will have drives, they will be controllable because we can set them, we can set goals for them by through those cost functions, so much more controllable than autoregressive models. And by designing those cost functions appropriately, we can make sure that those systems won't want to take over the world, and on the contrary, be subservient to humans and safe. And I'm going to stop here, and thank you very much for your attention.
Well, thank you very much, Jan, for the very insightful talk. I know it's very early in the morning, but we still like to spend another 10 minutes to entertain some questions.
Sure.
So I would like to invite Professor Zhu Jun who is our BAAI's chief scientist in machine learning and professor in Tsinghua University, to help me lead the Q&A session with you, Yang. Hopefully in 10 minutes, but the question may be long.
Sure.
Zhu.
Hello, hello, Professor LeCun. Nice to see you again. So it's my great honor to host the Q&A session. So first of all, thank you again for get up so early to deliver this very thoughtful and, as usual, very sharp talks with so many insight. So considering the time constraint, I selected a few questions. We have many questions we'd like to ask, but I selected a few to ask you. So as you said in the in your talk, so you say a few like issues about generative models. So many of them I also agree with you. But regarding the very basic principle of these generative models, I still have a question to you. So by definition, these generative models actually they often define to output a probability over multiple choices, right? In principle. So also, when we apply generative models, diversity and creativity is a desirable property. So we often package this model to output diverse results. So does that mean actually the factual error or logical error inconsistency is not avoidable for such models, even you have infinite data? Because in many cases, the data may have conflicting facts, right? So you also mentioned about uncertainty in the prediction. So that's my first question. So what's your thought on this? Yeah.
Right. So I don't think the issues with autoregressive prediction model, generative models, are fixable by preserving the autoregressive generation. I think those systems are inherently uncontrollable. And so I think they have to be replaced by the kind of architecture I'm proposing where you do, at inference time, you have the system optimize some cost and some criteria. That's the only way to make them controllable and steerable, and plan. Those systems will be able to plan their answer. When you're speaking, you're giving a speech like the one I just gave. You plan the course of the talk, right? You go from one point to another. You explain things. You're planning this in your head when you're designing the talk. You're not just improvising a talk one word after the other. Maybe at a low level you are improvising the words, but at a high level you're planning. So the necessity of planning is really obvious, and the fact that humans and many animals are capable of planning is really, I think, a intrinsic property of intelligence. So my prediction is that within a relatively short number of years, certainly within 5 years, nobody in their right mind would be using autoregressive LLMs. Okay, those systems are going to be abandoned pretty quickly.
Okay.
Because they're not fixable.
Yeah. Okay. So let's see. So I guess another related issue about the controllability. So in your design, actually, in your framework, a key component is the intrinsic cost module, right? So which is designed to basically determine the nature of the agent behavior. So I look at your working paper on the OpenRIO, and I share a common concern with one comment on the online. So it said that if this module is maybe not well specified, maybe the agent finally will get out of control, maybe do some dangerous actions. So do you have some feedback on this comment? Yeah.
Right. So I mean, certainly, if we build very powerful AI systems of the type that I described, the problem of designing those cost modules is not going to be easy. It's including sufficiently many guardrail cost modules that guarantee the safety of the system is not going to be a trivial task. But I think it's going to be a fairly straightforward task, something that will require a lot of careful engineering and fine-tuning and some of those costs may have to be trained as opposed to just designed. It's very much the same thing as a critic in reinforcement learning, or what's called a reward model in the context of LLM, right? So something that goes from the internal state of the system to a cost. You can train a neural net to predict a cost, and you train it by just exposing it to a lot of, making it produce a lot of outputs, and then have someone or something rate those outputs. And so that gives you a target for the cost function. And you can train a small neural net to compute that cost. And after you have it, then you can backpropagate to it to guarantee that this property is satisfied. So yeah, I mean, designing cost, I think we're going to have to move from designing architectures and designing prompts for LLM towards designing cost functions. Because those cost functions are going to be driving the nature of the behavior of our systems, okay? And contrary to some of my colleagues who are more negative about the future, I think this problem of designing the cost so that they are aligned with human values is eminently doable, and it's not something that, if we do it wrong once, it's not going to be the case that the AI systems are going to escape our control and take over the world, right? I mean, we will have a lot of ways to engineer those things pretty well before we deploy them.
Yeah, I agree with that. So, so another technical question is also related to this one is that I noticed that in your design of the the modules in the JPA or hierarchical JPA, so almost all modules are differentiable, right? So yeah, maybe you can use a big progression to train. But there are also another field like symbolic logic that can that represent a discrete maybe in some form can to formulate the constraint we like to put, for example, in the intrinsic cost module. So do you have some special consideration to bridge these two, or simply just ignore this a symbolic logic field? Yeah.
Right. So I think, yeah, I mean, there is a whole subfield of neurosymbolic architectures that try to combine, trainable neural nets together with symbolic manipulation and things like this. I'm very skeptical of those approaches because of the fact that symbolic manipulation is non-differentiable. So it's essentially incompatible with deep learning or with gradient-based learning, and certainly with gradient-based inference of the type that I described. So I think we should make every effort to use differentiable modules everywhere, including the cost functions. Now, there's probably a certain number of situations where the costs that we can implement are not differentiable. And for this, the optimization procedure that will perform the inference may have to use combinatorial optimization as opposed to gradient-based optimization. But I think that should be a last resort because zeroth order gradient-free optimization is much less efficient than gradient-based. So if you can have differentiable approximation of your cost function, you should use that as much as possible. To some extent, we do this already. When we train a classifier, the cost function that we want to minimize is the number of errors, right? But that's non-differentiable. So what we use is a proxy for that cost, which is differentiable, something like the cross entropy of the output, the log cross entropy of the output of the system with the desired output distribution, or something like E-square or hinge loss, right? So those are all upper bounds, basically, on the binary loss that is not differentiable, that we cannot optimize easily. So we're very familiar with this idea that we have to use cost functions that are differentiable approximations of the cost that we actually want to minimize. Okay,
yeah. So I guess my next question actually was inspired from our next speaker, Professor Mark Tegmark, who will give an on-site talk after you. So actually, we heard that you will attend a debate on the status and also the future of AGI. So as
right.
most of us will likely not be able to attend that debate, so can you share like some key points to us? So we pretty much maybe know your answer, but we want to hear some insight about that. Yeah.
Okay, so this is going to be a debate with 4 participants. So and the debate is going to be around a question as to whether AI systems are an existential risk to humanity. So Max, together with Yoshua Bengio, will be on the side of yes, it's possible that powerful AI systems may be existential risk to humanity. And then on the side of no will be myself and Melanie Mitchell from the Santa Fe Institute. And our argument is not going to be that there is no risk. Our argument is going to be that those risks, while they exist, are easily mitigated or suppressed through careful engineering. My argument for this is that, today, asking people whether we can make superintelligent system safe for humanity cannot be answered because we don't have a complete design for a superintelligent system, right? So until you have a basic design for something, you cannot make it safe. It's as if you asked in 1930, if you asked an aeronautical engineer, can you make a turbojet safe and reliable? And the engineer would say, what's a turbojet? Because turbojets had not been invented in 1930, right? So we're in a bit of the same situation. It's a little premature to claim that we're not going to be able to make those systems safe because we haven't invented yet. Now, once we invented them, we invent them, and maybe they will be on the, similar to the blueprint that I propose, then it would be worth discussing, like, how do we make them safe? And in my opinion, it would be by designing those objectives that are minimized at inference time. That's the way to make those systems safe. So obviously, if you imagine that the future of superintelligent AI system is going to be autoregressive LLMs, of course, you should be scared because those systems are not controllable and they'll, they may escape our control and spew nonsense. But the systems of the type that I described, I think, can be made safe. And I'm pretty sure that they will. So it will require careful engineering. It will not be easy. The same way it's not been easy over the last 6 decades or 7 decades to make turbojets reliable. The turbojets are incredibly reliable. You can cross large oceans with a 2-engine airplane now, and basically with incredible safety. And so that will require careful engineering, and it's very difficult. Most of us don't know how turbojets are designed to be safe. So it's not crazy to imagine that figuring out how to make a super intelligent AI system safe is difficult to imagine as well.
All right. So thank you, Yang, for the very insightful feedback. So as an engineer, I'm also a technician engineer. I have similar view. So thank you again, given considering time. Thanks a lot. Yeah, thank you.
Thank you so much.
Again, thank you very much, Yang, and also thank you, Zhujun, for the wonderful dialogue. And Yang, I'm not sure you can go back to sleep for a while, but again, thank you so much to wake up so early and deliver this wonderful, wonderful, very insightful talk. Thank you. 接下来，我们有请麻省理工学院人工智能与基础交互研究中心的教授和未来生命研究所的创始人 Max Temak 教授，在他的主旨报告中间，他将和大家一起探讨人工智能的安全问题，尤其是他的观点和刚刚勒控的观点是相对立的。It is my great honor to introduce our next keynote speaker, Professor Max Temak. Professor. Allow me to introduce a bit more. Professor Temak is a renowned physicist
and cosmologist. So he's not just an AI scientist, but he is first a physicist. And with that background, he has made quite some remarkable contributions to the understanding of our universe, and definitely later on artificial intelligence. In the field of AI, Professor Termak is a passionate advocate for the responsible development and deployment of AI technologies. He is the co-founder of Future Life Institute. I think many of us have read his very popular book, Life 3.0, which explores the potential impact of AI on humanity and the future of life itself. Most recently, Professor Termak initiated the petition to pause AGI research for 6 months. That was co-signed by about 1,000 scientists across the world, including a few sitting in this room. This petition has wakened up many governments and agencies, institutions, on the potential risk that the rapid development of AGI could bring to mankind. So today, Professor Termak will give a talk entitled, Keep AI Under Control. Max, the floor is yours.
谢谢你。
谢谢。
早上好。我会说一点普通话，可是我说的不好 ，so I'm going to switch to English. In Jan LeCun's beautiful presentation that you just saw, he also demonstrated that we must not trust our computers too much. And I want to talk today about how concretely we can make our computers more worthy of trust. But first, I want to say I'm so happy to be back in China. Many of my best students over the years at MIT, where I work, are Zhongguoren. And if you are interested in maybe coming to study at MIT and work with me, please apply. So how can we keep artificial intelligence under control? I love artificial intelligence. I'm so excited about all of the great opportunities that it gives us. And we've already heard this morning about so many wonderful things that we can do with artificial intelligence to help not just China, but to help the world. For example, basically all countries on Earth agree on the United Nations Sustainable Development Goals. We published a recent paper showing that artificial intelligence can make us reach almost all of these goals faster if we do it right and keep it under control. And I think we will then be able to even go quite far beyond these Sustainable Development Goals by curing or ultimately all diseases and helping create a future where everybody on Earth can live healthy, wealthy, and inspiring lives. If we keep the technology under control. As you know, there has been a lot of concern recently, though, about whether we actually will be able to keep it under control. For example, here is AI godfather Geoffrey Hinton just a few weeks ago.
Are we close to the computers coming up with their own ideas for improving themselves?
Yes, we might be.
And then it could just go fast.
That's an issue, right? We have to think hard about how to control that.
Yeah, can we?
We don't know. We haven't been there yet, but we can try.
Okay, that seems kind of concerning.
Yes.
And here is Sam Altman, the CEO of OpenAI that gave us ChatGPT. and GPT-4.
And the bad case, and I think this is like important to say, is like lights out for all of us.
So the bad case, he thinks, is lights out for all of us. All humans are dead. And these are not random people who know nothing about AI. These are some of the very leaders of the field, of course. And just on May 30th, this became world news, that an amazing list of AI researchers from around the world signed a statement saying that AI poses the risk of extinction. And you can see here that Jan LeCun is actually a minority among the Turing Award winners. He won the Turing Award together with Jeff Hinton and Joshua Bengio, who both think that AI could wipe out humanity. And Demis Hassabis, CEO of DeepMind, Sam Altman, CEO of OpenAI, and many, many prominent Chinese AI researchers you see here have also signed this. So why is it that so many people have this concern? And why are they talking about it now? Actually, the concern itself is very old as the idea of artificial intelligence. Alan Turing worried about things like this. Norbert Wiener worried about things like this. Irving J. Good, even long before I was born. Long ago, also 9 years ago, Stuart Russell, Stephen Hawking, Frank Wilczek, and myself worried about this. So it's not the concern is old, and it's kind of obvious, really, that if the most intelligent species on Earth has to deal with another entity that's more intelligent, that they might lose control. This is what happened with the woolly mammoth. This is what happened with the Neanderthals. We humans have already caused the extinction of many other species that were less intelligent than us, and because they lost control. If our goals were different from their goals and we needed their resources for our projects, they couldn't stop us because we were smarter. So the idea that we need to be careful to keep control of artificial intelligence that becomes smarter than us is very old. What is not old, what is new, is the urgency. Last time I was in China, 3 years ago, I showed this picture. I told you about this landscape of tasks where the elevation represents how difficult each task is for a machine, and the sea level represents what machines could do then. In the last 3 years, of course, the sea level has been rising a lot. Look how much has changed in just 3 years. Vinograd test, now computers can do quite excellent programming. They can even start doing quite interesting art. Many people are starting to write books with large language models. So the question of when we will reach artificial general intelligence, where AI can do all of these things, has really become much more urgent. Back when I was in, and that raises this other question. If we get machines that can do all our jobs, that means our jobs here also in the audience, AI development, which means that in the future, after AGI, we can replace ourselves by machines that can develop AI probably much faster. So instead of having to wait 1 year for the next version of things, maybe we have to wait 1 week or 1 day or 1 hour. And this raises the possibility of a recursive self-improvement where we soon get AI that's not just a little bit smarter than us, but way smarter than us. As much smarter than humans as we are smarter than a cockroach, maybe. Limited only by, ultimately, the laws of physics. But the laws of physics, they do limit intelligence. But You can't move information faster than the speed of light. You can't put too much compute in a small space, it'll turn into a black hole. But there's recent work on this showing that the limit is only about a million times above today's state of the art. So superintelligence could be very far beyond us. And what's basically happened, last time I was in China, there were still people who believed that we would not get artificial general intelligence for hundreds of years. Most AI researchers then still thought it would take decades, 30 years, 50 years. But now Microsoft has a paper out saying it's already starting to happen. They are claiming sparks of artificial general intelligence already in GPT-4. And many of my AI colleagues are wondering whether we will get AI this year, next year, 2 years from now. This is why people are talking about this now, even though the idea that it could be dangerous to have more intelligent beings we compete with is old. Here's what Joshua Bengio recently said.
We have basically now reached the point where there are AI systems that can fool humans, meaning they can pass the Turing test.
In other words, the Turing test, the idea that AI could master language, was something that long ago many researchers thought was going to be very close to the time when humans could do basically everything machines can, and he's arguing that large language models already can do this. So this might sound depressing. So many people are worrying. I want to point out there's something very good about this also. I'm actually quite hopeful that now that people take this seriously, it will lead to better relationships between East and West. Because before this, when people only took seriously the idea that AI can give you power, everybody wanted to compete, go as fast as possible, get it before the other one. But once it starts to become accepted that this could end civilization for everybody on Earth, it completely changes the incentives for the superpowers, for everybody. You know, it doesn't matter if you're American or Chinese, if you're extinct. And instead of thinking of it as an arms race, you can think of it then as a suicide race, where it doesn't matter who gets uncontrollable superintelligence first, because everybody dies at that point. So this, even though it might sound scary, I think for the first time, actually, now we have a situation where both East and West have the same incentive to continue building AI, get all the benefits, but not go so fast that we lose control. This is something we can all work together on. It's a little bit like climate change also, where the problems don't respect borders, where it's very natural to have partnership rather than collaborations. So this, I think, is actually hopeful. So how? For the rest of the talk, I want to discuss how we can keep AI under control, so we can build all these wonderful things and make sure they work for us, not against us. There are two main problems we need to solve. The first is alignment, how we make an individual AI actually do what its owner wants it to do. Jan LeCun's laptop was not so aligned because in the middle of his talk it crashed, right? The second problem is how can we also align all the organizations, the companies, the people, etc., around the world, so that their incentives are to use AI for good things and not for bad things. Because if we only solve the first problem and make very powerful AI widely available, we can have the situation where somebody, some terrorist or anybody else really who wants to take over the world and do things that you don't want, can use the technology to do this. So we'll talk a little bit about that also at the end. this is the realm of policy. But mostly, I want to talk about the technical problem of how you align the computer and AI to do what you want it to do. And there are many aspects to this that we will hear about from Stuart Russell and many other speakers here. I want to focus on the specific aspect of how you can better understand what's happening inside of these systems. There's the so-called field of mechanistic interpretability, which is a very strong form of interpretability. And after you understand it, change the system so that you can trust it better. This is a relatively young field and a very, very small field. I recently organized the largest conference in the world on this topic at MIT. Look how few people there are at my conference, compared to here, right? But I hope to convince you that this is a very promising and very exciting subject. And I would be very excited to collaborate with many of you on research projects in this. So, mechanistic interpretability. You train a neural network, an inscrutable black box that you don't understand, to do something intelligent. And then you try to figure out how exactly is it doing it. Why would you do this? Why do you want this? There are 3 different levels of ambition you could have. The lowest level of ambition is just to diagnose how trustworthy it is, to understand how much or how little should you trust it. For example, if you're driving a car, even if you don't understand how it works, you would at least like to know if you should trust the brakes or not. If you should trust that when you press this thing, it's going to slow down. The next level of ambition is to understand it better so that you can not just measure how trustworthy it is, but you can make it more trustworthy. And the ultimate level of ambition, and I'm very ambitious, so this is what I'm hoping for, is that we can actually extract all the knowledge in the black box that the machine learning has discovered and take it out and re-implement it in some other system where you can actually prove that it's going to do what you want. Stuart Russell might talk a little bit in his talk about proof-carrying code that can prove that it will run. It's a little bit like the opposite of a virus checker. If you have a virus checker on your laptop, if it can prove that your code you're going to run is malicious, it will refuse to run it. Otherwise, it will run it. Proof-carrying code is where the hardware asks the software to prove to it that it's going to do the right thing, and only if it can prove it, will it run it. And the vision here is to combine this with mechanistic interpretability, where you first discover the knowledge automatically by training a machine learning system, and then you use other AI techniques to extract out the knowledge and transform it into some form of proof-carrying code. We'll talk more about the details. But first, let me give you some examples to give you a flavor of how fast this field of mechanistic interpretability is progressing. So, for example, a recent paper we did in my MIT group, we've been working on this in my lab for about 7 years, was where we found that the knowledge in large language models is, to an interesting approximation, made of many, many little quanta, as we call them, pieces of knowledge that you can learn and study separately. We took gradients for individual tokens and just took the dot product of all the gradients and normalized them and made a similarity matrix. And then we did a spectral clustering. And as a result of this, we were able to automatically identify these quanta of knowledge that the large language model was learning. And what you can see here is a bunch of examples. Many of them are just facts. After a while, the neural network learns some fact where it becomes able to predict that this person's name is so-and-so, or this person worked at this company. And there are many quanta like that where there's just one thing you have to learn. For a small neural network, it's never able to learn it, so you have a high loss. But when you have a sufficiently large number of parameters that becomes able to learn it, then the loss goes to 0. We call those monogenic tokens. It's a little bit like a gene that tells you the color of your eyes, where it's just one thing that controls the trait you're interested in. There are other skills that neural networks have which require many quanta, and they tend to be learned more gradually as you scale. Here are some other examples of these quanta of knowledge that you automatically discover. It's not just facts. If you look at the examples on the left side, the large language model reads it, and the red or pink is always the predicted next token. You see, on all the examples on the left, what are they doing? What is it that the large language model has learned here? It's learned about numbered lists. And it's the same insight whether it's numbered in numbers or with letters or hexadecimal. On the right side, it's learned something very different. It's learned that people like to write lines sometimes that all have roughly the same length. So it starts to predict the pink line break, hit return, when the line becomes that long. There's a very wide variety of quanta we find. And interestingly, we find that the large language models we looked at, they always tend to learn the quanta when you train kind of in the same order. It first learns the most useful things and then less useful things. It's a little bit like a child. First you learn to crawl, then you learn to walk in the same order. And the more data you have, and the more parameters you have, the more compute you have, the more quanta you learn in this sequence. And from this, we're actually able to make an interesting prediction for why we get these scaling laws. It's well known that the loss you get drops like a power law with respect to compute, with respect to data set size, and number of parameters. And all of these three can be explained at the same time if you just assume that the frequency distribution of those quanta skills that you need also are a power law, like a Zipf law. And we have a little formula for how these different scaling laws relate to each other. An interesting part of mechanistic interpretability is to extract how the knowledge is represented inside of the model. For example, Professor David Bao's group in Boston at Northeastern, they recently discovered how GPT stores the fact that the Eiffel Tower is in Paris. And they figured out how it was represented. And they were able to edit those weights in the neural network so that when they came to tell it that it was in Rome instead, not Paris. And then when they asked, hey, where is the Eiffel Tower? It started explaining all sorts of things there about Rome. And they also discovered how it's stored. It's actually in a very, very simple way. It was linearly encoding it. Basically, you have a matrix, an MLP inside of the transformer, and when you multiply it by the vector that encodes Paris, out comes the vector encoding Rome with a large coefficient. We have, there's been many, many nice papers in the last half year by many groups discovering how different kinds of knowledge are stored. We've done a lot of work at MIT looking at how algorithmic information gets represented. So if you have some kind of abstract multiplication table like this, maybe ordinary multiplication, maybe some other group operation, and you simply want to predict what happens when you combine two elements like this. You want to predict, for example, all the red examples, and you have a test set with all the held back green examples, but with a much bigger table here than just 5 by 5. How does that work? So here's a simple example we did, where the operation is you have to do plus. modulo 59. So you take basically two photos of images in pixels or something like that, and you send them in. And you know that any group operation can always be represented as a group of matrix multiplications. So we train an encoding into matrices, and then we train a decoder for how to decode it. And then we look inside. How is this represented in the high-dimensional internal space as it's being trained? And all of a sudden, eureka! The neural network had an insight. All the points fall on a two-dimensional hyperplane in the embedding space as a circle. And if you think about modular addition, it's just like if you have a clock with all the numbers 1, 2, 3, 4, up to 12, where if it's 11 o'clock plus 2 hours, it's 1 o'clock. It sort of starts over. It discovered this, and when it discovered this, it became able to generalize and solve examples that it had not seen before, because this representation that it came up with automatically embeds that this operation is commutative and associative, and it can exploit this to fill out the rest of the table. If you just do ordinary addition without the modular part, then you find that it will start representing all the entities in a line, not the circle. If you overfit, you see it represented in some random, stupid way, so it can always repeat back the training data, but it can never generalize. Grokking is a case where it takes a very long time to generalize, and if you train in a situation where it fails to learn anything and is always confused, the embeddings don't even change. We can also use machine learning to try to force the solutions to become simpler and easier for us to understand. Normally, there are many, many different ways in which a neural network could do the same task. We want the simplest one, but it will normally learn one of the more complicated ones, because there are more complicated than simple ones. So, for example, if you look at the human brain, it is very modular. We do vision here, hearing here, et cetera, so that neurons that need to communicate a lot are close together. That's because in the brain, it's very expensive if the brain has to send signals during a long distance. It takes up more space in the head, uses more energy, causes time delay. But in a neural network, and a fully connected feed-forward neural network, you can permute the order of all the neurons in the layer without changing the loss function at all. And it doesn't change any of the usual regularizers either. So here, we don't encourage our artificial neural networks to become simple. So we made a simple test. We had an idea. What if we add a loss function, a regularizer, to the neural networks, a little bit like L1 norm, where we penalize, again, weights to make it sparse, but we also multiply this by the distance between neurons. So we embed each neuron in a point, embed the neurons actually in a real space, 2 dimensions or 3 dimensions or whatever. And we penalize, so it costs more to have long connections. And look what happens. You train a neural network, for the example we just looked at, and after a while it gets not just much more sparse, but you start to see structure. It has modules, this one, this one, this one. These are a bit like these quanta that we talked about earlier. And interestingly, we can look at each of them, what they do. This one does that circle, discovered the circle trick that we talked about. This one discovers a different way of doing it. And then they combine together at the top in a kind of error correction. A little bit like majority voting with 3 votes to become even more accurate. So, and this worked beautifully also for many other examples we tried. Here we tried, instead of a modular addition, we tried permutation, the permutation group of 24 elements. So you permute, and it made a very simple neural network. it's well known, you can think of this as permuting the four corners of a tetrahedron. So there is a 9-dimensional representation of this group corresponding to the 3x3 matrices that you can use to rotate the tetrahedron onto itself and flip it. Sure enough, it discovered that you only need 9 neurons here at the beginning to get perfect accuracy. And moreover, this matches, it rediscovers a lot of the group representation theory we can study in mathematics class. For example, it discovered that this neuron here is either 0, -1, or 1, depending on whether it's an even or odd permutation, whether it reflects the tetrahedron or not. When we looked at formulas, when we train a neural network to predict simple functions, and again penalize long connections, it simplifies to the point where you can see that it's much easier for humans to interpret. The equation on the left, for example, it outputs 2 different things. The first thing only depends on x1, x2, and x4. The second thing only depends on x1 and x3. And even though in the beginning it's just a big mess, at the end, you can see it actually learned to simplify this into 2 completely independent neural networks that don't talk to each other, which are much easier to understand separately. On the next one, there's feature sharing. When you look at it a bit, you can see now, oh, first, what's happening is it's learning to square the numbers. And then it's combining them. For the third one, you can see everything combines into 1 neuron. That's the stuff under the square root. And then it learns to calculate the square root in the last step, because we're plotting the activation of that 1 neuron on the x-axis against the output, and it's exactly the square root function. This works for larger systems also. This is what happens with MNIST. And these are small examples, but I think this is an what I want you to take away from this is we humans don't have to spend so much time figuring out how neural networks work if we can train them to simplify themselves first. It gets a lot easier. In this case, what we had was we saw that neural networks are often unnecessarily complicated because you have this permutation symmetry that you can do any permutations of the neurons in a layer without increasing your loss. And by removing that symmetry, you get simplicity, you get modularity. Another kind of unnecessary complication in many neural networks is continuous. So if you have a feed-forward neural network that does something really intelligent and accurate, you can put in any continuous nonlinear transformation of your data if it's invertible with some layers, and then you can have some more layers that remove that transformation. And it's still going to perform the same, but maybe it'll be more complicated. So with this awesome grad student from Beida, Liu Ziming, we were able to get some good results on this, where it could simplify itself over all of these different continuous transformations I mentioned and discover, for example, hidden symmetries in the problem. We applied it to a very famous physics problem of black holes. When Carl Schwarzschild discovered black holes in 1915, he thought that you would die when you reached the event horizon. Because if you look at the formula here, this so-called metric tensor that describes the shape of space-time, you divide by r minus 2m. So when r equals 2m, you divide by 0. That sounds terrible. Maybe you die. No. 17 years later, Gullstrand and Panlevey discovered that you can just continuously transform the coordinate system. This was a stupid coordinate system that Schwarzschild found. There's a better one where you see that nothing dangerous happens. There's no division by r minus 2m. You only have a singularity at r equals 0. It took them 17 years to discover this. Our automated AI tool discovered that in 1 hour. That there was a way of dramatically simplifying this famous physics problem. Since I have the pleasure to be in China, I have to say a little bit about AlphaGo, AlphaZero, etc., which of course made lots of news when we were told that it was better than humans at playing Go and chess. Here also there's been some very interesting work on mechanistic interpretability. This team at Google DeepMind discovered by taking millions and millions of games, or game positions, and letting stockfish, the chess program programmed by humans, calculate the value of each position, how much material do you have, etc., and to see, was it true or not that AI, that AlphaZero had automatically rediscovered these things? And they found yes. The AI had actually automatically discovered by itself that a bishop is worth about 3 pawns, and a rook is worth about 5 pawns, etc. And it even automatically discovered a lot of more sophisticated measures of value in chess. And just like the example with the Eiffel Tower in Rome, here you found actually it was very easy for humans to extract it. You could linearly decode it with just a softmax layer, the information that was in there. Related, Stuart Russell and colleagues wrote a very important paper showing that we should not trust AI too much unless we can prove it. Because you were all told that you can never defeat AI in Go, right? And you probably believed it, because even Kaji could not defeat it, right? But that was wrong, it turned out, because this paper, they found they could do an adversarial attack against these Go programs by placing a little trap and tricking the computer into surrounding your stones, and then you start to surround the computer at the same time as it's surrounding you. A computer would not notice that if this was a big enough group. And then at the end, poof, you just win. And one of the people on the team was able to beat the world's best Go program more than 50% of the time without using any computer. So don't trust AI systems that are supposed to be very powerful unless you can prove it, which is my vision for mechanistic interpretability. Jan LeCun mentioned in his talk this idea that maybe large language models lack a world model. I hear many people say that, but I think that's not true. And here's a really beautiful paper showing this. This is a transformer that's been trained, a large language model that's been trained to play a game which is much simpler than Go, the game of Othello. Actually, all they did was they gave it a bunch of games written out like this. They just gave it the sequence of moves and trained it to predict the next move, okay? They did not tell it anything about the rules of the game or that it's played on a board and in a world or anything like that. But then they were able to, with mechanistic interpretability, nonetheless discover that inside this transformer, it had built a model of the world. It was an 8x8 two-dimensional world. The board with pieces on it. And it did this just because it turned out that by having a good world model, it was easier for it to do the task it was trained. And I think you see in the same way when you use Baidu's Ernie Bot or GPT-4 or anything like that, it's clearly able to model a little bit different people. If you start writing in a certain style, it will try to continue in that style. So large language models can build models of what's outside of them. One last example that I want to highlight here about progress in mechanistic interpretability, it has to do with one of the ultimate ways of understanding what a neural network does, which is replacing the whole thing by a formula, a symbolic formula. This is called symbolic regression. If I give you a spreadsheet, a table of numbers, and I ask you to predict the last column from the other columns as a symbolic formula, that's symbolic regression. If it's a linear function, that's linear regression. It's super easy, right? You just invert a little matrix. But if it's an arbitrary nonlinear function like this, this problem is probably non-NP hard, exponentially hard, because there are exponentially many possible formulas of length n symbols. So we worked a lot on this in my group at MIT and found that the vast majority of the formulas we actually care about in science and engineering are modular, meaning that a function of many variables can be written as a combination of functions with fewer variables. And we discovered that if you first train a black box neural network to accurately fit the function, then just by studying the gradients of your black box and looking for certain algebraic properties, you can uncover any modularity, even quite complicated, without knowing what the modules are. And that lets you break apart the complicated problem into many, many simpler ones that you can then solve. So for example, here I gave it a data table to see if it could fit the formula for the kinetic energy according to Einstein's relativity theory. And I'm showing you on the x-axis how complicated each formula is, and on the y-axis how bad an approximation it is. So we're most interested in the convex corners, which are both simple and accurate. So it discovered the correct one, but it also discovered this approximation, which you probably all learned in high school or earlier, Newton's approximation, mass times speed squared over 2. And we tried it on a large number of equations from all sorts of physics textbooks, and we actually got state-of-the-art performance on this task of symbolic regression simply by leveraging the power of neural networks. So the incredible power that a black box has to learn, but we didn't stop with that, right? That was step one. And then once you have the neural network that has discovered the knowledge and the data, you do these other steps to extract out the knowledge. So in summary, I hope I've convinced you that the mechanistic interpretability is a very fun field, a very promising field. And let me also try to convince you that it will continue to be fun and promising. It's a lot like neuroscience, where you have a system that can do your brain, which can do very intelligent things, but which is a black box that we don't understand, right? Except this is much easier than neuroscience. Because when you do normal neuroscience, here in Tsinghua, Daxue, or Beida, you can only measure maybe 1,000 neurons at a time out of hundreds of billions. And you have to get special permission from some ethics board to do experiments on humans. And there's noise. When you do mechanistic interpretability, you can measure every neuron all the time, every weight. You'd have no ethics board. You could even build your own organisms and try things. And as a result, even though very few people have worked on this field for a very short time, it's making progress much, much faster than traditional neuroscience. And this gives me hope that if more of us join this field, we can make very, very rapid progress moving forward and go far beyond the first ambition level of just figuring out whether to trust things or not and making them maybe a little bit better. I really think that the third and most ambitious option here, making something that's guaranteed trustworthy, will be possible. Let me just say one more thing to try to persuade you that it's not hopeless to have something much more intelligent than us that we can prove is safe. First of all, we don't have to write the proof ourselves, right? We can delegate to an AGI or a superintelligence to write the proof because it is much easier to check that a proof is correct than to discover the proof, right? So if the machine gives you a very, very long proof, you can write your own program in Python, which is so short and simple that you completely understand it, that checks that whole proof, is like, yep, that's right, I trust it, I can run it. And similarly, you might think, oh, if it takes one graduate student 1 year to write one paper about something, this does not scale. But all the tools I showed you here almost in mechanistic interpretability were automated, where you can make a machine do all the hard work. You can train the neural network to simplify itself first, and then you can use other automated tools to figure out what has it really learned, how is it really doing it, and come up with methods of doing something which is just as intelligent, but where you can actually guarantee safety. And this, to me, is very hopeful, because I will never trust something much more intelligent than us unless I can prove it. But if I can prove it, I will trust it, because no matter how smart it is, it cannot do the impossible. So this offers an opportunity to really keep control over systems that are much more intelligent than us. We use these techniques to make them prove their own trustworthiness, and then we only run the ones where we actually have proofs. To finish, let me just say a few words also about the second part. If we have these machines that will obey the person who controls the machine, how do we make sure that people or companies don't do bad things with their own machines? This is, of course, the question of policy. So let's listen again to Joshua Bengio.
That is both very exciting because of all the benefits we can bring.
I should add, he was talking, as you remember, about that we now have passed the Turing test. And what does that mean?
That is both very exciting because of all the benefits we can bring with socially positive applications of AI, but also I'm concerned that powerful tools can also have negative uses, and that society is not ready to deal with that. And that's essentially why we are saying, let's slow down. Let's make sure that we develop better guardrails.
So this letter is saying, let's pause, which was mentioned earlier. I want to be clear, it does not say we should pause AI. It does not say that we should pause almost anything that we heard about here so far in this conference. We should continue doing almost all the wonderful research that you're all doing. It just says that we should pause development of systems more powerful than GPT-4. So this would mainly be a pause for some Western companies right now. And the reason for that is that these are precisely the systems that can lead us the fastest towards losing control. Having super powerful systems that we don't understand enough, the purpose of the pause is just to make artificial intelligence a bit more like biotech. You know, in biotech, you cannot just, if you're a company, say, hey, I have a new medicine I've discovered. I'm going to start selling it in every supermarket in Beijing tomorrow. No. First, you have to persuade experts from the Chinese government or the American government that this is a safe drug, that its benefits outweigh the harms. There's a review process. Then you can do it. If we establish guardrails like this for those AI systems that have such great power that they really could cause harm, potentially, then we will become like biotech, right? There's a level playing field, not the race to the bottom. We go a little bit slower, but as a result, everything we have is safe. Will this destroy innovation? Well, let me ask you this. Did the biotech innovation get destroyed by the fact that you have to get approval for your medicines? Of course not. We live in a golden age of biotech. It's, in fact, precisely the fields that have too weak regulations on the dangerous things, which instead often destroy the innovation. Like civilian nuclear power, investments in this have basically collapsed, at least in the West, after Fukushima for example, right? It would have been much better if they had been a little more careful and not had Fukushima and Chernobyl, so we could have all had the benefits. Let's not make that mistake. Let's become more like biotech with our most powerful systems, not like Fukushima and Chernobyl. And I want to end by just saying that I feel that China really has a unique opportunity to contribute to safe and wise governance of artificial intelligence. You know, both the upsides and the risks of very powerful AI, like superintelligence, of course, will be shared by all humanity. So no country can tackle this alone. And China, I think, is really uniquely positioned because China is a world-leading science and technology power, so it can help lead research, therefore, not only on how to make AI powerful, but also how to make it robust and trustworthy. This is what I've talked about, right? And since China's international influence is growing, together with its ability to inspire and the power to shape the global AI agenda, including AI regulation, China's voice is really, really important. I also think that an advantage China has over the West is that China has, you have one of the oldest surviving civilizations, right? In China, 200 years is a short time, not a long time like it is in America. And there's a stronger tradition in China of really thinking long term for that reason. And there's also quite a tradition of, therefore, being safety-minded. So, for example, I was so happy just last week, I think, seeing China's Global Security Initiative actually explicitly talking about preventing AI risk. And I really welcome this kind of Chinese wisdom and leadership so that we can have a wonderful future with AI by keeping it under control. Thank you. 谢谢你们.
Well, thank you so much, Max, for the very thought-provoking talk. We do want to keep you here for another 10 minutes, so let me invite my old friend and chair professor from Tsinghua University to have a dialogue with you. Yaqing, please. 我们下面有请清华大学讲席教授、智能产业研究院院长张亚勤博士和这个 Max 有一个10分钟的互动。
All right, thank you, Hong Zhang. Max, nice to see you again. Okay, nice to see you again.
Nice to see you.
That was certainly a very informative and enlightening talk. And I want to first thank you for your leadership and the championship in raising the awareness of AI risks and challenges.
谢谢你。
谢谢你。Well, we talk about two types of wisdom, and those two types of wisdom are in a race. One is the wisdom to invent new things, new technologies, human creativity, including AI. The other wisdom is ability to control it, right, to make sure it's steered to the direction for the human and the societal benefits. And obviously, in your opinion, we are kind of behind. The number two is behind. I remember you organized a number of events, and of course with the organization, the Future Life Institute, and also the 23 principles in the Salomon AI conference. That was 2017, right?
Yes.
So my question is, compare with back then, 2017, do you think the gap between number one, number two has expanded, or it has become narrower?
I think, unfortunately, it's expanded. So, compared to 5 years ago, or even 2020 when I was in China last time, what we've seen is the growth of power of AI has gone faster than many people expected. Most of my colleagues in 2020 did not expect that we would pass the Turing test in 2023. And the wisdom, it's gone a little bit slower than we would have liked. And this is exactly why there's more interest now in pausing the most risky work, exactly to give a chance for the wisdom to catch up.
In your book, Life 3.0, I'm a big fan of the book. So is my son. You talk about 3 stages of life, right? Life 1.0 is the most primitive form of life that started 4 billion years ago. And life 2.0 is where we are. Right? It's a Homo sapien. It's a human, but with a civilization, language, and all the all the system we have right now. So, and the Life 3.0 is AGI. It's machine intelligence. You call it super intelligence, and that of course involves both the thoughts, the culture, the software, and also the hardware. And where do you think we are? How close we are? And do you want to change your definition of Life 3.0? Well, it's pure carbon or it's a mixture of carbon and silicon?
We humans, maybe, you're already maybe Life 2.1, 2.2, because we can put in a pacemaker, cochlear implants, and maybe some of our children are so connected to their phones, they're almost part of
between 2 and 3.
Yeah, but it's important to remember that on one hand, Life 3.0, it's a very inspiring idea, right? The idea that after spending the first 200,000 years or so of human existence really being disempowered, just trying to not get eaten, trying to not starve to death, having very little control of our future, we've now, because of science and technology, become the captain of our own ship, kind of the master of our own destiny. That's exciting, I think. And we see that if we continue this trend with better AI, closer to Life 3.0, we can also do so much more. Instead of having silly fights on this little spinning ball in space about who should have this little territory there and that, we have this incredible cosmos with so much resources where we can flourish for billions of years. All of those things are very hopeful to me and motivating. But it's important to remember that Life 3.0 is not one thing. It's just like the next step. The space of possible Life 3.0 forms, the space of artificial minds is vast. And we have a lot of choice in what kind of Life 3.0 we go to. I personally love humanity, human beings, humanity. I think I would like to steer towards a future with Life 3.0 that has compassion, has emotions, has feelings, cares about some of the things we care about. Not some kind of zombie, totally unconscious machines that all they care about is something that we consider very banal. I think those are all real possibilities. So I would like to be empowered and not just sit here with you and we eat popcorn and we wait and see what comes, but ask ourselves, what do we want to come, and then steer in that direction.
So it will be an ideal combination of human intelligence and machine intelligence to the best of the world.
It's all possible, but it's not happening automatically. It will happen because the people here think hard about where we want to go, and then we work hard to steer in that direction. That's how we get.
Max, you were born in Sweden, right? You grew up in Europe, and you live and you teach in the U.S. You travel around the world, and you talk with a lot of Chinese colleagues. So let me ask you a question that the AI governance, the state of AI governance. If you rate the level, the state of AI governance with a scale of 1 to 10, 10 being the best, how would you rate China, Europe, and the United States?
I think I love this question, by the way. One of my favorite quotes that I identify with is the Dutch Renaissance scientist Christian Huygens. He said that science is my religion and the world is my country. I feel that's why. And so if we look at the world itself, I think first of all we should give a grade to all of humanity. I think it's pretty low. I think we can do much better. I think China of these three has so far done the most in terms of regulating AI. Europe is number 2. We've worked a lot with the Future Life Institute on educating policymakers in Europe now that they're finishing the EU AI Act, for example, and America is in third place. I think that if we can make Europe, if we can help Europe come up with really sensible regulation, it's likely America will follow them. We saw this happening with GDPR, for example. The Americans didn't want to really do anything much like that for privacy, but then Americans started to get much less spam after the European Union passed these laws. And then it started to get more popular also in America.
Right. Well, Max, your career spanned mathematics, physics, neuroscience, and of course, artificial intelligence. In the future, obviously, we will depend increasingly on the interdisciplinary capability and knowledge. We have a lot of graduate students, a lot of prospective young people. What is your advice to young people in terms of how they make their career choices?
My advice, first of all, is...
In the age of AI.
Yeah, focus on the basics, because the economy and the job market will change ever more rapidly. So we're moving away from this paradigm where you study things for 12 years or 20 years, then you do the same thing for the rest of your life. It's not going to be like that. It's much more important that you're strong on the basics and are very good at creative, open-minded thinking, so that you can be nimble and go with the flow. And of course, pay attention to what's happening all across AI, not just in your own field, because it's in the job market, the first thing that will happen is not people getting replaced by machines, but people who do not work with AI will be replaced by people who work with AI. Yeah. Can I add one more? Just I see the time is blinking there, but I just want to say something optimistic. I think Jan LeCun was teasing me a little bit. He calls me a doomer. But if you look at me, I'm pretty happy and cheerful, actually, and I'm actually more optimistic than Jan LeCun about our ability to understand future AI systems. I think that's very, very hopeful. I think if we go full steam ahead and just give ever more control away from humans to machines that we don't understand, that will end very badly. And that's, but we don't have to do that. I think if we work hard on mechanistic interpretability and many of the other technical topics you'll hear here today, we can actually make sure that all this ever more powerful intelligence works for us and use that to create an even more inspiring future than science fiction writers used to dream of.
Yeah, talk about Jan LeCun, just 1 minute. And I have a huge respect for Jan, and he's a pioneer. We did a lot of work following his pioneer work.
Yeah, me too.
But one thing I disagree, just to cause a little bit of debate, and he talked about system 1 to system 2, right? And think AI already passed system 1 and is really trying to make system 2 work in Daniel Kahneman's taxonomy. I actually have a different view. I think system 2 is probably AI can achieve in the foreseeable future. System 1 is actually the hardest, because that is the instinctive capability that we don't even know how to inference, how to reason. And just like autonomous driving, I spent a lot of time working on the self-driving cars. And you can learn how to drive a car, but once you learn, it is that muscular memory, it's that instinct, system 1, that actually give you that edge, right? And that's why we have issues, troubles with our AI system.
Yeah.
That's also, if you read the book Search Memory by Eric Kendall, he talked about explicit decision and implicit decision corresponding roughly to system 1 and 2. Would you agree with me or with Jean?
No, I think you make a very good point there, and this is something I think we probably both agree with Jan LeCun about also, is that the architectures will change again. Now everybody's like, oh, transformers. But I'm quite confident that when we get artificial general intelligence and superintelligence, it's going to look nothing like a transformer. Rather, some of the things developing now will be can maybe be at best be components in other systems. You already have things like Auto GPT, where people put loops around large language models and complement what they can do with a lot more traditional machine learning. One thing which is also very obvious from almost all the work in mechanistic interpretability so far is that every time we figure out how a large language model does something, we're like, oh my God, that's so stupid. I can do it much better. So it kind of discovers the minimum viable solution. It does 3 lousy algorithms, and then it does error correction and makes them vote or whatever. So I think mechanistic interpretability will not only give us things that AI that we can trust because we can prove it ultimately, but it will also be more efficient.
So it's quant agnostic, the algorithms or the models?
Yeah, so more broadly, I envision in the future that we use these powerful black box neural networks as sort of a mining for algorithms, and it discovers all these different algorithms and how they
the
put
definitions is independent, agnostic. Yeah.
But then you put them together in like the optimal way.
Right.
And then you start getting systems which are just both much more efficient and simple and reliable and trustworthy. And we kind of know it's going to end this way, because even though Ernie Bot and ChatGPT and the different flag models we heard about here are all great, they look how many watts of energy they use. Your brain can do so much that they cannot on 20 watts.
Right.
Yeah.
Yeah. In the interest of time, we have to end the dialogue. But let me just say this: it is super powerful AI, but it is timely and it is necessary to put that into control. I use your word to end this. Let us get empowered by AI, not overpowered by AI. All right. Thank you.
谢谢你。
谢谢。
Well, thank you both very much. And well, one last question, Max. Earlier on, we mentioned there will be a debate between you and Lacombe. When will that happen?
June 22 in Toronto.
6月22号，多伦多，我们可以经历一下 Max 和那个 Lacombe 的这个对话，然后辩论on the future of AI. Oh, thank you.
It will be fun. 谢谢你。
再次感谢 Max， 感谢雅琴，也同时再次感谢今天上午所有到的分享的嘉宾和各位来宾、各位朋友。到此呢，本届智源大会的开幕式接近尾声。在今天下午和接下来的一天里边，我们希望大家能够参与更多的大会的环节，各个分论坛、各个对话，不留遗憾，满载而归。现在我宣布，2023年北京智源大会开幕式到此结束，感谢各位的参与，谢谢。
嘿。